Welcome to the Sleepy Scientist. It's wonderful to have you here. Before we begin, let me know where in the world you're watching from tonight. Are you tucked away in a quiet bedroom, riding home on a late train, curled up on the sofa with a blanket and something warm to drink? Wherever you are, I hope you're comfortable, safe and ready to drift gently into one of the strangest questions in science. If you enjoy these relaxing journeys through the universe, a like and subscribe really helps this sleepy little channel keep floating along. And to everyone already subscribed, thank you. Truly, your support means more than you know. Now, tonight's topic might be a little dangerous for bedtime because it begins with one of the biggest questions science can ask, and then quietly suggests the answer may not be quite as settled as it first appears. But not to worry. The universe has been expanding for billions of years, so it can probably wait patiently while you get comfortable. So let's begin, shall we? Why might the universe be older than we think? And what does it really mean to measure the age of everything, from inside everything itself? The universe is usually said to be about 13.8 billion years old. It is one of those numbers that appears so often in science books, documentaries, museum displays, and quiet late-night searches that it can start to feel almost fixed, like a date stamped neatly onto the side of reality. 13.8 billion years, not 13.7, not 14. A number with just enough precision to sound reassuring, as though the universe has been measured, filed, and politely placed back on the shelf. But this number is not a final answer carved into stone. It is the best current estimate, built from many different kinds of evidence, and held together by the most successful model scientists presently have. It comes from studying ancient light, the expansion of space, the temperature of the cosmos, the distances between galaxies, the behavior of matter, and the mathematical structure of modern cosmology. There is no giant clock floating somewhere beyond the Milky Way, ticking away with unusual dedication. No cosmic grandfather clock has been discovered in the constellation of Orion, which is probably for the best because winding it would be inconvenient. Instead, the age of the universe is inferred. That word matters. To infer something means to work it out from clues. The clues are real, measurable, and often astonishingly precise, but they are still clues. Scientists do not watch the birth of the universe directly. They look at what remains. They study light that has travelled for billions of years. They measure how galaxies move away from one another. They examine the faint afterglow of the early universe, known as the cosmic microwave background. They compare observations with models that describe how space, time, matter, radiation, gravity, and expansion should behave. That is why the age of the universe feels strange as a concept. When the age of a tree is measured, rings can be counted. When the age of a fossil is estimated, radioactive decay can provide a clock inside the material itself. When the age of a person is asked, someone may produce a birth certificate, although whether anyone can find it in the right drawer is another matter entirely. But the universe contains the trees, the fossils, the people, the drawers, and the slightly hopeless search through old paperwork. Measuring its age means measuring the history of the whole stage on which every other clock exists. The broad scientific framework behind this estimate is the Big Bang model. Despite the name, the Big Bang was not simply an explosion into empty space. It is better understood as the early hot, dense state of the universe, followed by the expansion of space itself. Everything was once compressed into a far hotter, denser condition, and over time the universe expanded, cooled, and allowed matter to form the structures seen today. Atoms, stars, galaxies, planets, and eventually creatures curious enough to ask slightly rude questions about where all of this came from. The idea that the universe changes over time was not always obvious. For much of scientific history, many thinkers assumed the universe might be eternal and essentially static on the larger scales. Stars seemed to wheel overhead, planets wandered in their familiar paths, and the heavens gave the impression of grand permanence. Then, in the 20th century, that picture began to shift. Georges Lemaitre, a Belgian physicist and priest, used Einstein's general theory of relativity to argue that the universe could be expanding. He proposed that if the universe is expanding now, then it must once have been smaller, denser, and hotter. Around the same period, Edwin Hubble studied distant galaxies and showed that many of them appeared to be moving away from us, with more distant galaxies generally receding faster. This pattern became one of the central observational foundations for the expanding universe. It did not mean Earth was at the centre of everything, receiving a dramatic cosmic farewell from every galaxy. Rather, it suggested that space itself was stretching, so that galaxies separated by vast distances were carried farther apart as the universe evolved. From that discovery came a powerful idea. If the universe is expanding, then scientists can try to trace that expansion backward. They can ask what the universe looked like when galaxies were closer together, when matter was hotter and denser, and when the light now reaching telescopes first began its long journey. This is one of the main ways cosmic age enters the story. The universe's age is not simply guessed from how old everything looks. It is estimated by reconstructing the expansion history of space. Still, this reconstruction depends on models. A model in science is not a decorative miniature of the universe with tiny galaxies glued on, although that would be charming. It is a structured explanation that uses mathematics and observation to describe how nature behaves. In cosmology, models include assumptions about ordinary matter, dark energy, radiation, gravity, and the shape and expansion of space. When the observations fit the model well, scientists gain confidence. When they do not fit perfectly, the interesting part begins. This is where the number 13.8 billion years becomes more intriguing. It is not a weak number. It is not a casual guess. Measurements from the cosmic microwave background, especially from missions such as the European Space Agency's Planck spacecraft, strongly support an age close to 13.8 billion years within the standard model of cosmology. That model has explained a remarkable amount, from the large-scale structure of galaxies to the faint temperature patterns left in ancient light. Any claim that the universe is older must deal honestly with the strength of this evidence. But the story is not perfectly simple. Some measurements of the universe's expansion rate do not fully agree with one another. Observations of very distant galaxies by the James Webb Space Telescope have revealed surprisingly bright and developed systems from very early cosmic times. Ancient stars and early black holes can sometimes seem uncomfortably mature for their place in the timeline, at least before the uncertainties are carefully examined. These discoveries do not prove that the universe is older. They do, however, make the neatness of the number feel less final. The central question, then, is not whether scientists have made an obvious mistake. That would be too easy, and the universe rarely chooses the easy option when a more puzzling one is available. The deeper question is whether the universe is actually older than the standard estimate suggests, whether its earlier structures formed faster and more efficiently than expected, or whether the models used to interpret the evidence still need refinement. Each possibility is fascinating in a different way. If the universe is older, then one of the most basic measurements in modern science would need to be reconsidered. If the early universe evolved faster, then the first stars, galaxies, and black holes may have been far more energetic and efficient than once imagined. And if the models need adjustment, then the age of the universe may remain close to 13.8 billion years, while the story around that number becomes richer, stranger, and more precise. So the number that seems too precise is not wrong simply because it is precise. It is precise because science has become astonishingly good at listening to faint clues from deep time. But precision is not the same as completion. A number can be accurate within a model and still leave questions around the edges. The universe may be telling a story that is mostly understood, partly unfinished, and just old enough to make every human lifetime feel like a candle flickering briefly in a cathedral of time. Trying to date the universe is unlike trying to date almost anything else. A rock can be held, sliced, tested, and compared with other rocks. A fossil can be placed into a geological layer, measured against radioactive decay, and given a place in Earth's long, patient archive. Even an ancient star can be studied by its light, its mass, its brightness, and the chemical traces hidden in its atmosphere. But the universe is not one object sitting conveniently inside a laboratory. The universe is the laboratory. It is the stage, the scenery, the props, the actors, the dust in the spotlight, and the slightly baffled audience trying to work out when the theatre opened. That is what makes Cosmic Age such a delicate idea. When scientists ask how old the universe is, they're not asking how old one thing inside the universe happens to be. They're asking how long the whole observable cosmic story has been unfolding since the early hot, dense state described by the Big Bang model. This is not a question that can be answered by finding a single ancient object and reading its age like a label. Even the oldest stars and galaxies are still younger than the wider cosmic setting that allowed them to form. They are clues, not clocks that started before everything else. On Earth, age can often be measured by processes that happen at steady, predictable rates. Radioactive decay is one of the most important examples. Certain unstable atoms transform into other atoms over time, and they do this according to measurable half-lives. A half-life is the time it takes for half of a sample of a radioactive isotope to decay into another form. This allows scientists to estimate the ages of rocks, meteorites, fossils, and archaeological materials depending on which radioactive elements are present and what time range is being studied. Carbon dating is useful for once-living material over thousands of years. Uranium lead dating can reach back across billions of years. It is not magic, although it can feel suspiciously close when a lump of ancient mineral quietly tells a story older than every human city. But the universe cannot be dated by taking a sample from the beginning and placing it in a machine. There is no small piece of the Big Bang kept in a drawer labelled "Please return by Friday." Instead, cosmologists use several different methods that overlap and correct one another. They study how fast space is expanding. They measure how long light has travelled from distant objects. They model how stars age and how long different kinds of stars can survive. They examine the cosmic microwave background, the faint afterglow of the early universe, which carries information from a time when the cosmos was only a few 100,000 years old. Each method answers part of the question, but none of them is quite as simple as looking at a birthday candle and counting the wax. Expansion tells scientists about the history of space itself. Light travel time tells them how far away and how far back certain objects appear. Stellar evolution tells them whether the ages of the older stars make sense within the larger cosmic timeline. Background radiation gives a snapshot of the young universe, revealing its temperature patterns, composition, and geometry. Together, these clues form a kind of cosmic cross-examination. The universe is not being asked politely how old it is. It is being questioned by photons, stars, galaxies, and mathematics. One of the most important principles behind this is that looking farther into space usually means looking further back in time. Light travels extremely fast, but not infinitely fast. In empty space, light moves at about 300,000 kilometers per second. That is fast enough to circle Earth several times in a single second, which is generally considered showing off. Yet across cosmic distances, even light takes time. The light from the moon takes a little over 1 second to reach Earth. The light from the Sun takes a little over 8 minutes. The light from the nearest major galaxy, Andromeda, takes about 2.5 million years. So when Andromeda is observed, it is seen not exactly as it is now, but as it was around 2.5 million years ago. For the most distant galaxies, the effect becomes far more dramatic. Some light-reaching modern telescopes began travelling when the universe was young, before Earth existed, before the Sun formed, before the Milky Way looked the way it does today. Telescopes are therefore not only instruments for seeing across space, they are also instruments for seeing into the past. A deep image of the universe is partly a time machine, though regrettably one with no return ticket, no snack trolley, and no ability to warn earlier galaxies about their future telescope fame. This does not mean every distant object reveals the age of the universe directly. A galaxy whose light has travelled for billions of years tells scientists how that galaxy looked when the light left it. To turn that observation into a place on the cosmic timeline, researchers need to understand distance, redshift, expansion, and the model connecting them. Redshift is especially important because the expansion of space stretches light as it travels, shifting it toward longer, redder wavelengths. The greater the redshift, generally speaking, the farther back in cosmic time the object is being observed. Here, Albert Einstein becomes essential. His general theory of relativity, published in the early 20th century, changed the way science understands gravity. Instead of treating gravity simply as a force pulling objects through fixed space, general relativity describes gravity as the curvature of space-time caused by mass and energy. Space and time are not a rigid background. They are part of the physical universe, able to bend, stretch, and evolve. This idea is not just philosophical decoration. It is the mathematical foundation of modern cosmology. General relativity allows scientists to describe an expanding universe in a serious physical way. It connects matter, energy, space, time, gravity, and motion into one framework. Without it, the age of the universe would be much harder to define. The question is not only how fast galaxies are moving, but how the fabric of space itself has changed over time. Matter slows expansion through gravity. Dark energy appears to accelerate expansion. Radiation mattered more in the very early universe. Dark matter shaped the growth of galaxies and large-scale structure. All of these ingredients affect the route from the hot early universe to the cool, vast cosmos seen today. This is why dating the universe requires more than one clock. The expansion rate gives one kind of evidence. The oldest stars provide another. The cosmic microwave background offers a deeply ancient snapshot. The large-scale distribution of galaxies preserves traces of early sound waves in the hot young cosmos, known as baryon acoustic oscillations. Supernova help reveal how expansion has changed over time. None of these alone is the entire answer, but when they agree, confidence grows. When they disagree, even slightly, cosmologists pay close attention. The question therefore becomes wider and more interesting than simply asking how old the universe is. It becomes a question about what kind of evidence could answer something so enormous. What can light reveal after travelling across billions of years? What can ancient stars tell us about the minimum age of the cosmos? What can the expansion of space tell us about the beginning of the observable universe? And how much of the answer depends on the model used to connect all these clues together? The age of the universe is not measured by one clock ticking in the dark. It is assembled from many clocks, some made of atoms, some made of stars, some made of stretched light, and some made of equations describing space and time themselves. That is why the familiar number feels both powerful and fragile. It rests on evidence gathered from across the observable universe, yet it also reminds us that the deepest measurements in science are often not simple acts of reading. They are acts of reconstruction. The universe leaves traces of its past everywhere. but it does not arrange them in order. Scientists have to gather the pieces, compare them carefully, and ask not only how old everything is, but how anything could know. For a long time, the universe looked as though it might be still. Not still in the small local sense, of course. Planets moved, moons circled, comets made alarming entrances and then vanished again, like celestial guests who'd forgotten to say where they were going. Stars rose and set as Earth turned beneath them. But on the larger scales, the universe itself was often imagined as something fixed and permanent, a grand cosmic backdrop, filled with stars and nebulae, quietly existing in a kind of eternal arrangement. That picture began to change when astronomers learned to treat light not only as something that lets objects be seen, but as something that carries information. Starlight and galaxy light are not just brightness arriving at a telescope. They are messages. Hidden inside them are patterns that reveal motion, temperature, chemical composition, and distance. The universe, rather thoughtfully, sends receipts. They are just written in wavelengths instead of ink. One of the first great clues came from Vesto Slipher, an American astronomer working at Lowell Observatory in the early 20th century. Slipher studied the light from spiral nebulae, which were mysterious fuzzy objects in the sky. At the time, astronomers were still debating whether these nebulae were small structures inside the Milky Way or entire star systems far beyond it. By splitting their light into spectra, Slipher measured how their light was shifted. He found that many of these objects showed a strong shift toward the red end of the spectrum. This shift became one of the most important clues in modern cosmology. Redshift means that light has been stretched toward longer wavelengths. A simple way to imagine it is to think of sound. When an ambulance passes by, the pitch of the siren changes. As it moves toward you, the sound waves are squeezed closer together and the pitch sounds higher. As it moves away, the waves are stretched out and the pitch sounds lower. Light behaves differently from sound in many important ways, but the rough idea is helpful. When a source of light is moving away, or when space itself stretches while the light travels, the light can arrive shifted toward longer, redder wavelengths. Slipher's measurements showed that many of these spiral nebulae seemed to be receding at remarkable speeds. This was a strange result. It hinted that the universe was not simply a static arrangement of objects sitting calmly in space. Something larger was happening. But the full meaning of the pattern needed another piece of information. Distance. That is where Edwin Hubble enters the story. In the 1920s, Hubble used observations from the Mount Wilson Observatory in California to study Cepheid variable stars in distant spiral nebulae. Cepheid variables are stars whose brightness rises and falls in a regular pattern, and because of work by Henrietta Swan Leavitt, astronomers had learned that their rhythm could be used to estimate their true brightness. Once the true brightness of a Cepheid was known, its apparent faintness could reveal its distance. It was a brilliant cosmic measuring tool, like finding a lighthouse with a known lamp strength shining across a very dark sea. Hubble's observations helped show that some spiral nebulae were not small clouds inside the Milky Way at all. They were other galaxies, vast systems of stars far outside our own. The Milky Way was no longer the entire known universe. It was one galaxy among many, which must have been a humbling moment for humanity, although humanity has had quite a lot of practice at being gently moved away from the centre of things. Hubble then compared distances with redshifts. He found that the farther away a galaxy was, the faster it generally appeared to be receding. This relationship became known as Hubble's law. It suggested that galaxies were not simply flying randomly through space like sparks from a fire. Instead, space itself was expanding, carrying galaxies away from one another on the larger scales. The universe was not static, it was evolving. This idea can be misunderstood easily. so it is worth moving gently. The expansion of the universe does not mean galaxies are flying outward from one central point into empty space. There is no known central location from which everything exploded. The better picture is that the space between distant galaxies is stretching. Wherever an observer is located, distant galaxies will generally appear to move away, because the distances between large-scale regions of space are increasing. The universe is not expanding into something in the ordinary sense. Space itself is part of what is expanding. A common comparison is dots drawn on the surface of a balloon as the balloon inflates. The dots move farther apart not because they are crawling across the rubber, but because the rubber between them stretches. This comparison is useful, though imperfect, because the real universe is not the surface of a balloon and does not require someone outside it with suspiciously powerful lungs. Still, it helps capture the main idea. Distant galaxies separate because the fabric of space changes over time. This expansion gave scientists one of the first ways to estimate cosmic age. If galaxies are moving apart now, then in the past they must have been closer together. If the expansion is traced backward, the universe becomes denser and hotter, leading toward the early state described by the Big Bang model. The present-day expansion rate is called the Hubble constant. Despite the word constant, measuring it precisely has turned out to be anything but emotionally relaxing for cosmologists. The Hubble constant describes how fast the universe is expanding today. In broad terms, it tells scientists how much faster a galaxy appears to recede for each additional amount of distance. If that expansion rate is high, then the universe seems to have reached its present size in less time. If the expansion rate is lower, then the universe may have taken longer to arrive at its current state. So the Hubble constant is directly connected to estimates of cosmic age. This simplest intuition is almost like rewinding a film. Imagine watching galaxies drift apart. If they are separating very quickly, then rewinding the motion brings them close together after a shorter interval. If they are separating more slowly, rewinding takes longer. This is not the whole story because the universe has not expanded at one steady speed forever. Gravity from matter slowed expansion in the past, while dark energy appears to have caused expansion to accelerate more recently. Radiation also mattered far more in the early universe than it does today. The cosmic film does not rewind at one neat speed. It has changing tempo, unusual lighting, and a plot written by general relativity. Even so, the basic clue remains powerful. Expansion turns the universe into something with a history. It means the cosmos is not merely a place, but a process. It has changed temperature, it has changed density, it has changed structure. There was a time before galaxies like the Milky Way existed, a time before stars, a time before atoms, and a time when the universe was so hot and dense that ordinary ideas of empty space become difficult to picture. This is why Hubble's observations were so important. They helped transform cosmology from a study of where things are into a study of how everything has changed. Slipher's redshifts showed motion hidden in light. Hubble's distance measurements revealed a pattern in that motion. Together, they gave scientists one of the first great clues that the universe itself has an age. And yet, that clue also leads directly into the uncertainty at the heart of the question. If the age of the universe depends partly on the expansion rate, then measuring that rate matters enormously. A slightly different value can imply a slightly different history. A disagreement between methods can become more than a technical inconvenience. It can become a sign that something in the story is not fully understood. The expanding universe, then, is both a triumph and a puzzle. It gives scientists a way to look backward toward the beginning of the observable cosmic story. But it also reminds us that the age of everything is tied to the behavior of space itself, and space is not a passive emptiness. It stretches, responds, curves, and evolves. The universe is not sitting quietly in time. In a very real sense, time, space, matter, and light are all woven into the same slow unfolding. The expanding universe gives scientists a way to trace cosmic history backward, but there is another clue, softer and stranger, that fills the sky in every direction. It is not a galaxy, not a star, not a planet, and not a single object at all. It is a faint glow left over from when the universe was young, so stretched and cooled by cosmic expansion that it now arrives mostly as microwave radiation. This ancient glow is called the cosmic microwave background. The cosmic microwave background is often described as the oldest light scientists can observe across the whole sky. That does not mean it comes from the exact first moment of the universe. It is not a photograph of the Big Bang itself, which would be a little too convenient and would probably still be out of focus. Instead, it is light from a time when the universe first became transparent. Before that, space was filled with a hot, dense plasma of charged particles, mostly free electrons and atomic nuclei. Light could not travel far without constantly scattering off those free electrons. The young universe was bright, hot, and opaque. More like a glowing fog than a clear night sky. As the universe expanded, it cooled. Eventually, after roughly 380,000 years, conditions changed enough for electrons and nuclei to combine into neutral atoms, especially hydrogen and helium. This process is called recombination, although the name is slightly misleading because it was really the first major formation of neutral atoms in the universe. Once those neutral atoms formed, light no longer scattered so constantly. Photons could travel freely through space. The universe became transparent, and the light released at that time began a journey that has continued for billions of years. That ancient light is still arriving today, but it no longer looks like visible light from a hot young universe. Space has expanded enormously since the moment that light began travelling freely, and as space expanded, the wavelengths of the light stretched too. What began as a hot glow has cooled into microwave radiation with a temperature of only about 2.7 degrees above absolute zero. In voiceover terms, that is extremely cold, although technically still warmer than absolute nothingness, which is the sort of achievement only the universe would bother to mention. The story of its discovery is one of the loveliest accidents in modern science. In 1965, Arno Penzias and Robert Wilson were working with a large horn antenna at Bell Telephone Laboratories in New Jersey. They were trying to understand a persistent background noise in their instrument. The signal seemed to come from every direction. It remained no matter where the antenna was pointed. They checked equipment, considered possible interference, and even dealt with pigeon droppings inside the antenna, because science sometimes advances through majestic theory and sometimes through cleaning up after birds. At the same time, nearby researchers were thinking seriously about relic radiation from the early universe. The possibility had been predicted earlier by Ralph Alpher and Robert Herman, building on work connected to the hot Big Bang model. They argued that if the universe had once been hot and dense, there should still be a cooled remnant glow left over from that early state. Penzias and Wilson had found exactly the kind of signal this idea predicted, though they had not been looking for it in quite that way. Their discovery became one of the strongest pieces of evidence for the Big Bang model, and later earned them the Nobel Prize in Physics. The cosmic microwave background matters because it is not just ancient light. It is ancient light with a pattern. At first glance, it looks almost perfectly uniform, arriving from every direction at nearly the same temperature. That smoothness tells scientists that the early universe was remarkably even on large scales. But hidden within that smoothness are tiny temperature variations, slight differences from place to place, only about 1 part in 100,000. These tiny ripples are incredibly important. They are the early fingerprints of structure, the subtle density differences that would eventually grow into galaxies, galaxy clusters, and the immense cosmic web. Several missions have mapped this glow with increasing precision. NASA's Cosmic Background Explorer provided early detailed measurements that confirmed the near-perfect blackbody spectrum of the cosmic microwave background and detected its tiny temperature variations. Later, NASA's Wilkinson Microwave Anisotropy Probe mapped the whole sky with far greater precision, allowing scientists to estimate the universe's age, composition, and geometry more accurately. Then the European Space Agency's Planck mission refined the picture even further, giving the most detailed all-sky map of these ancient temperature patterns so far. These missions turned the cosmic microwave background into one of the strongest anchors for the modern estimate of cosmic age. By studying the size, strength, and distribution of its temperature variations, scientists can infer what the universe contained when it was young and how it has evolved since. The patterns reveal the amounts of ordinary matter, and dark energy needed to match the observed universe. They also help show that space appears very close to flat on large scales, meaning its overall geometry follows the rules of ordinary straight-line geometry to a remarkable degree, at least across the observable universe. From this information, combined with the standard model of cosmology, scientists arrive at an age of about 13.8 billion years. This is why that number is not a casual guess. It is tied to real measurements of the oldest widespread light available. The cosmic microwave background is not merely a faded glow. It is a record of the universe when it was young enough that galaxies had not yet formed, stars had not yet switched on, and the raw ingredients of cosmic structure were only beginning to leave their delicate imprint. Yet, as powerful as this evidence is, it also depends on interpretation. The cosmic microwave background gives scientists a snapshot of the universe at one ancient moment. To turn that snapshot into a full history, researchers must use a model that describes how the universe expanded, cooled, and changed from then until now. If the model is correct, the ancient light points strongly toward the familiar age. If some ingredient is incomplete or misunderstood, the same light could be asking a more complicated question. This is what makes the cosmic microwave background so beautiful and so humbling. It is both a foundation and a boundary. It shows that modern cosmology is not simply guessing in the dark. It is listening to a signal that has crossed nearly the entire history of the observable universe. But it also reminds us that the earliest directly visible light is not the beginning itself. It comes from after the universe had already changed dramatically. Before that glow was released, there were hundreds of thousands of years hidden inside an opaque cosmic fog, and before that, conditions so extreme that ordinary intuition becomes very quiet indeed. So when scientists say the universe is about 13.8 billion years old, the cosmic microwave background is one of the deepest reasons they can say it with confidence. It is the cooled afterglow of a younger universe, stretched across the sky, carrying a pattern from a time before stars. But it is not the final page of the mystery. It is an ancient clue, perhaps the best one available, whispering that the universe has a measurable age, while also reminding us that the story began before the oldest light could travel freely. The cosmic microwave background gives scientists one of the oldest pictures the universe allows, but a picture alone is not the same as a complete story. To turn that ancient glow into an age, a composition, and a history, cosmologists need a framework. They need a model that can explain how the universe began in a hot, dense state, how it expanded, how matter gathered into structure, and how the vast cosmic web of galaxies eventually appeared. The standard model used for this purpose is called the lambda cold dark matter model. The name sounds slightly like something that escaped from a physics department after midnight, but its meaning is quite specific. Lambda refers to the cosmological constant, a term connected to dark energy, the mysterious influence that appears to drive the accelerated expansion of the universe. Cold dark matter refers to a form of unseen matter that moves relatively slowly compared with the speed of light and helps build cosmic structure through gravity. Together, these ideas form the backbone of the most successful large-scale model of the universe currently available. The lambda cold dark matter model describes a universe made of several very different ingredients. There is ordinary matter, the stuff made from atoms, stars, planets, dust, gas, people, teacups, and the occasional telescope mirror being nervously polished. Ordinary matter is real and familiar, but it makes up only a small fraction of the total cosmic budget. Most of the matter appears to be dark matter, which does not emit, absorb, or reflect light in any normal way, but reveals itself through gravity. Galaxies rotate as if they contain far more mass than can be seen. Galaxy clusters bend light from objects behind them more strongly than visible matter alone can explain. The large-scale structure of the universe also fits much better when dark matter is included. Vera Rubin was one of the key scientists who made dark matter difficult to ignore. In the early 20th century, she studied the rotation curves of galaxies, especially spiral galaxies. According to what might be expected from visible matter alone, stars farther from a galaxy center should orbit much more slowly than stars nearer the center. Instead, Rubin and her collaborators found that outer stars often move surprisingly fast. The galaxies behaved as though they were embedded in huge invisible halos of mass. This did not prove every detail of dark matter, but it provided powerful evidence that something unseen was shaping the motion of galaxies. Then there is dark energy, which is stranger still. In the late 20th century, two teams studying distant Type 1a supernovae discovered that the expansion of the universe is accelerating. Saul Perlmutter led the Supernova Cosmology Project, while Brian Schmidt and Adam Rees were key figures in the High Z supernova search team. Their observations showed that distant supernovae were dimmer than expected in a way that suggested the universe's expansion had not merely continued, but had sped up over time. This discovery changed cosmology profoundly, because gravity from matter should tend to slow expansion, not accelerate it. Something else seemed to be at work. The simplest explanation within the standard model is the cosmological constant. Albert Einstein originally introduced the cosmological constant into his equations of general relativity for a different reason, at a time when a static universe still seemed plausible. After the expanding universe became accepted, the term was often treated as unnecessary. Yet in modern cosmology, it returned in a new role, not to hold the universe still, but to describe a steady form of dark energy associated with empty space itself. The universe, it turns out, has a talent for making old mathematical terms look unexpectedly useful again. The lambda cold dark matter model also includes cosmic expansion and the early conditions inferred from the cosmic microwave background. The tiny temperature variations in that ancient light are not random decoration. They reveal the early distribution of matter and radiation. They show the seeds from which galaxies and galaxy clusters later grew. By comparing these patterns with predictions from the model, scientists can estimate how much ordinary matter, and dark energy the universe contains. They can also infer the geometry of space and the timeline of expansion. This is where the familiar age of about 13.8 billion years enters the picture. That number is not simply read directly from the cosmic microwave background like a date printed on an old photograph. It comes from fitting observations into the lambda cold dark matter model. The model takes the early universe revealed by the cosmic microwave background, applies the known physics of expansion, gravity, radiation, matter, and dark energy, and traces how the universe should develop over time. When the pieces are fitted together, they point to an age close to 13.8 billion years. The success of this model is remarkable. It explains the cosmic microwave background with impressive precision. It matches the broad distribution of galaxies across enormous distances. It accounts for the growth of structure from tiny early ripples into the cosmic web. It explains why ordinary matter alone cannot build galaxies quickly enough. It includes the accelerating expansion revealed by distant supernovae. For a model describing the entire observable universe, that is not a bad afternoon's work. But success is not the same as completion. The lambda cold dark matter model works extremely well, yet two of its main ingredients remain deeply mysterious. Dark matter has not been directly identified as a specific particle or substance. Dark energy is even less understood, and the cosmological constant may be a placeholder for something deeper. The model describes what the universe appears to do, but not always why its hidden ingredients have the properties they seem to have. This matters for the age question, because the age of the universe depends not only on what is observed, but on how those observations are interpreted. If the model is correct in all essential ways, then 13.8 billion years remains strongly supported. If some part of the model is incomplete, the interpretation could shift. The universe might not need to be older in a simple sense, but its early behavior, expansion, history, or hidden ingredients may require a more subtle explanation. So the standard model of cosmology is both a foundation and a reminder. It gives science a powerful way to turn ancient light into a cosmic timeline. It makes the universe measurable across billions of years. Yet it also leaves room for caution, because the most precise number in the story depends on a model that still contains darkness, acceleration, and unanswered questions quietly holding the whole structure together. Even with a powerful standard model, the universe still has a way of leaving small stones in the path. One of the most important is known as the Hubble tension. It is not a tension in the dramatic sense, with galaxies glaring at one another across a conference table, although cosmologists at conferences may occasionally achieve something similar. It is a tension between two ways of measuring how fast the universe is expanding today and the fact that they do not quite agree. The expansion rate of the universe is called the Hubble constant. It describes how quickly distant galaxies appear to be moving away from us as space itself expands. This number matters because it is tied directly to the history of the universe. If space is expanding faster today, then tracing that expansion backward can suggest a shorter time, since the universe was in its earlier, denser state. If space is expanding more slowly, then the timeline can stretch longer. In the real universe, the calculation is more complicated because expansion has changed over time, shaped by matter, radiation, dark matter, and dark energy. But the basic connection remains. Expansion and age are woven together. The strange part is that scientists can measure the Hubble constant in more than one way. One method begins with the early universe. It uses the cosmic microwave background, the ancient afterglow from when the universe first became transparent. Missions such as the European Space Agency's Planck spacecraft map this radiation in exquisite detail. By studying the tiny temperature variations in that light, scientists can infer the ingredients and expansion history of the universe within the lambda cold dark matter model. This method tends to give a lower value for the present expansion rate. Another method begins much closer to home. It uses the local distance ladder, a chain of measurements that starts with nearby stars and gradually reaches outward to other galaxies. This ladder depends on objects whose distances and brightness can be understood well enough to use them as cosmic measuring tools. Two of the most important are Cepheid variable stars and Type 1 supernovae. Cepheid variable stars are especially beautiful because they pulse in a regular rhythm. Their brightness rises and falls over days or weeks, and that rhythm reveals their true brightness. This crucial relationship was discovered by Henrietta Swan Leavitt in the early 20th century. She studied Cepheid variable stars in the Magellanic Clouds and found that the longer a Cepheid's period of brightness variation, the more luminous it truly was. This period luminosity relation became one of astronomy's great measuring tools. Once the true brightness of a Cepheid is known, astronomers can compare it with how bright it appears from Earth and work out how far away it is. This was not just a useful trick, it changed the scale of the universe. Cepheids helped Edwin Hubble show that some spiral nebulae were actually separate galaxies far beyond the Milky Way. They became rungs on a ladder leading out into the deep universe. Later, Type 1a, supernovae added another powerful rung. These exploding stars can be used as standardizable candles because their light can reveal their intrinsic brightness in a predictable way. They are visible across enormous distances, making them valuable for measuring cosmic expansion far beyond the reach of nearby stars. Modern distance ladder work has been led in part by Adam Rees and the Shoes team, whose name stands for Supernovae Hubble for the equation of state of dark energy. The team uses observations from the Hubble Space Telescope, and more recently the James Webb Space Telescope, to refine distances to Cepheid variables and supernova host galaxies. Webb's infrared vision is especially useful because it can reduce some problems caused by dust and crowded star fields. In other words, it helps astronomers see through a few of the universe's more annoying curtains. The surprising result is that this local distance ladder method tends to give a higher expansion rate than the value inferred from the cosmic microwave background. The difference is not enormous in everyday terms, but in precision cosmology it is large enough to matter. It has persisted through many improvements in measurement, which is why it is called the Hubble tension rather than the Hubble mild inconvenience. This tension is important because the two methods are looking at the universe from different ends of time. The cosmic microwave background method begins with the early universe and uses a model to predict the expansion rate today. The distance ladder method measures the nearby universe more directly, using stars and supernova to build outward. If the two do not agree, then something needs explaining. Perhaps one or both methods contain subtle measurement errors that have not yet been fully identified. Perhaps the calibration of distances still hides a small bias. Perhaps the standard cosmological model is missing a piece of physics. That last possibility is the one that makes the question so intriguing. The Hubble tension might be hinting that the expansion history of the universe is not perfectly described by the current model. It may involve dark energy behaving in a more complicated way than a simple cosmological constant. It may point toward new physics in the early universe, such as an additional energy component that briefly affected expansion. Or it may eventually settle down as observations improve, becoming one of those scientific mysteries that quietly packs its bags after better data arrives. But until then, it matters for the age of the universe. The age estimate of about 13.8 billion years is deeply connected to the expansion history inferred from the standard model. If the expansion rate today, or the expansion behavior in the past, is not fully understood, then the age calculation may depend on assumptions that need refinement. This does not mean the universe is definitely older. It means the route by which scientists arrive at its age is still being tested. The Hubble tension is therefore not a simple sign that cosmology is broken. It is more like a careful tap on the glass. It tells scientists to look again at the measurements, the models, and the hidden assumptions connecting ancient light to the present-day universe. The number 13.8 billion years remains strongly supported, but the disagreement reminds us that even the most successful cosmic timeline is still a living piece of science, not a finished inscription on the wall of eternity. To measure the expansion of the nearby universe, scientists first have to measure distance. That sounds simple enough until the distances involved stop being the kind a person can walk, drive, fly, or emotionally process. In ordinary life, distance can be measured with a ruler, a tape measure, or the slightly unreliable method of saying something is about 5 minutes away, which can mean almost anything depending on traffic, footwear, and optimism. In astronomy, the objects are too remote for direct contact, so distance must be built step by step. This is the cosmic distance ladder. It is not one single method, but a chain of linked methods, each one reaching a little farther than the last. The nearby universe is measured with techniques that work close to Earth. Those measurements then calibrate brighter objects that can be seen farther away. Those brighter objects calibrate still more distant markers, until astronomers can estimate distances across millions and even billions of light years. The ladder begins nearby and stretches outward into deep space, rung by rung, with each rung depending on the strength of the one below it. The first major rung is parallax. Parallax is the apparent shift in the position of a nearby object when viewed from two different places. You can see a small version of it by holding up a finger and closing one eye, then the other. Your finger seems to jump against the background, not because it has become ambitious, but because your viewpoint has changed. Astronomers use Earth's orbit around the Sun in a similar way. By observing nearby stars from opposite sides of Earth's orbit, they can measure a tiny apparent shift against more distant background stars. From that shift, they can calculate distance. Modern parallax measurements have been transformed by the European Space Agency's Gaia mission. Gaia has measured the positions and motions of more than 1 billion stars in the Milky Way with extraordinary precision. This matters because nearby stellar distances form the foundation for much of the distance ladder. If the bottom rung is stronger, the higher rungs can be calibrated more confidently. Gaia is therefore not just making a beautiful map of our galaxy. It is helping astronomers sharpen the measuring tools used far beyond it. Beyond parallax, astronomers rely on standard candles, objects whose true brightness can be known or estimated. Cepheid variable stars are among the most famous. These stars brighten and dim in a regular pattern, and their pulsation period is connected to their true luminosity. Henrietta Swan Leavitt discovered this period luminosity relation, turning Cepheids into vital distance markers. If a Cepheid's true brightness is known, its apparent brightness reveals how far away it is. A dim-looking Cepheid may not be weak. It may simply be very far away, quietly doing its job across an unreasonable amount of space. Another useful rung comes from red giant stars, especially a method known as the tip of the red giant branch. Low-mass stars eventually become red giants, and at a certain stage their brightness reaches a fairly consistent upper limit before helium begins fusing in their cores. By identifying this feature in a population of stars, astronomers can estimate the distance to the galaxy containing them. This method provides an independent check on Cepheid-based distances, which is important because science prefers not to balance the universe on one ladder if another ladder is available nearby. Farther out, Type 1, as supernovae become essential. These are powerful stellar explosions associated with white dwarf stars in certain systems. They are not perfectly identical, but their light curves can be standardized, meaning their changing brightness over time helps reveal their true luminosity. Because Type 1a supernovae are so bright, they can be seen in galaxies far beyond the range of individual Cepheid variables. They became crucial for measuring cosmic expansion and for the discovery that the expansion of the universe is accelerating. Then come galaxy redshifts. As space expands, light from distant galaxies is stretched toward longer wavelengths. The greater the redshift, the more the light has been stretched during its journey. Redshift is not by itself a simple distance measurement for every object, because cosmic expansion has changed over time, and galaxies also have their own local motions. But when redshift is tied to calibrated distances from supernovae and other methods, it becomes a powerful way to study the expansion of the universe on large scales. The fragile part is that each rung depends on careful calibration. A small uncertainty near the bottom can influence the rungs above it. If nearby parallax distances are slightly off, Cepheid distances can be affected. If Cepheid distances shift, then the calibration of Type 1a supernovae can shift. If supernova distances shift, then measurements of the Hubble constant can shift. It is a calm, cosmic version of measuring a room with a slightly stretchy tape measure. The room may still be measured carefully, and the result may still be very useful, but the stretch must be understood, or every later measurement inherits a little of the problem. This does not mean the distance ladder is weak. It is one of the great achievements of observational astronomy, built through patient measurement, repeated checks, and increasingly precise instruments. The issue is that cosmology has reached a level of precision where small differences matter. A tiny correction that once seemed harmless can become important when scientists are comparing the local expansion rate with the early universe prediction from the cosmic microwave background. That comparison is at the heart of the Hubble tension. Local measurements using Cepheid variable stars, Type 1a supernovae, and related distance ladder techniques tend to find a higher present-day expansion rate than the value inferred from the early universe using the cosmic microwave background and the lambda cold dark matter model. If the distance ladder contains an unresolved calibration issue, then the tension may eventually shrink. If the ladder is correct, and the early universe measurement is also correct, then the disagreement may point toward unknown physics. This matters for the age of the universe because expansion is one of the main clocks cosmologists use. The inferred age depends on how fast the universe is expanding now and how its expansion changed in the past. Local measurements are not just local facts, they help test the entire cosmic timeline. If nearby galaxies suggest one expansion rate while ancient light suggests another, then the universe is asking for a more careful explanation. So the distance ladder is both practical and profound. It begins with nearby stars shifting by tiny angles in the sky, and reaches outward to exploding stars in remote galaxies. It connects the local neighborhood of the Sun to the age of the cosmos itself. Each rung is a reminder that measuring the universe is not a single grand leap, but a patient climb, where even the smallest step must be trusted before the next one can carry us farther into time. Another way to test the age of the universe is to look for the oldest things inside it. This may sound obvious, but it is a powerful idea. Nothing inside the universe should be older than the universe itself. A star cannot sensibly be born before the cosmic conditions that allowed stars to exist. A galaxy cannot form before matter has had time to gather under gravity. Even the oldest object must still fit inside the larger timeline that contains it. So, ancient stars become a kind of cosmic archaeology. They are not pieces of the Big Bang itself, but they are surviving witnesses from very early times. Their light carries information about their temperature, mass, age, and chemical composition. Some have been shining quietly for more than 10 billion years, outlasting entire generations of larger, brighter stars that burned through their fuel quickly and disappeared. If the universe had an attic, these stars would be the dusty boxes at the back, labelled in handwriting so old nobody wants to throw them away, just in case they are important. Stars age in different ways depending mainly on their mass. Massive stars burn through their nuclear fuel quickly, sometimes living only a few million years before ending in dramatic supernova explosions. Smaller stars burn slowly and can survive for many billions of years. This is why the oldest surviving stars are usually low-mass stars. They're faint, patient, economical objects, cosmic candles that learned early on not to spend all their fuel at once. By studying them, astronomers can place lower limits on the age of the universe. If a star is 12 or 13 billion years old, then the universe must be at least older than that star. One important place to find ancient stars is inside globular clusters. Globular clusters are dense, roughly spherical collections of stars that orbit galaxies, including the Milky Way. They can contain hundreds of thousands or even millions of stars packed into a relatively small region. Many globular clusters are extremely old, making them valuable records of early star formation. They are like ancient villages orbiting the outskirts of galaxies, crowded, bright, and full of stars that formed long before the sun existed. Globular clusters matter because their stars often formed around the same time and from the same original cloud of gas. This makes them useful for studying stellar evolution. When astronomers observe a globular cluster, they can compare the brightness and colour of many stars together. They can see which stars have already moved away from the main part of their lives and begun evolving into later stages. This pattern helps estimate the cluster's age. The oldest globular clusters in the Milky Way are generally thought to be more than 12 billion years old, which places them very close to the early history of the galaxy, and not too far, cosmically speaking, from the beginning of star formation itself. But the most famous ancient star in this discussion is HD 140283, often nicknamed the Methuselah star. It is located in the Milky Way and has attracted attention because some earlier estimates suggested it might be older than the universe, or at least uncomfortably close to it. That would be a serious problem if taken literally. A star older than the universe would be like finding a cake older than the kitchen, which would raise questions about both baking and reality. The important phrase, though, is earlier estimates. Stellar ages come with uncertainty. HD 140283 was not truly proof that the universe was older than scientists thought. Instead, it became a famous example of how difficult it can be to measure the ages of very old stars. Later work refined its estimated age and uncertainties, bringing it into better agreement with the standard cosmic timeline. The star remains extremely old, but not a clean contradiction of a universe about 13.8 billion years old. Part of the challenge is distance. A star's distance affects how its brightness is interpreted. If a star is slightly farther or closer than assumed, its true luminosity changes, and that can alter age estimates. This is one reason missions such as the European Space Agency's Gaia spacecraft are so important. By measuring stellar positions and distances with extraordinary precision, Gaia helps sharpen the basic information needed to understand stars. A better distance can make an old star less mysterious, though thankfully not less beautiful. Chemical composition is another key uncertainty. Stars are made mostly of hydrogen and helium, but they also contain small traces of heavier elements. Astronomers often call these heavier elements metals, even when they are things like oxygen or carbon, because astronomy enjoys simplifying chemistry in a way that would make chemists blink slowly. The amount of heavy elements in a star tells scientists something about when it formed. Very old stars usually have very low metallicity because they formed before many generations of stars had created and spread heavier elements through space. The chemical content of a star affects how it burns fuel, how bright it is, and how it evolves. If the composition is not known accurately, the age estimate can shift. Brightness and temperature also matter. astronomers compare real stars with stellar evolution models, which describe how stars of different masses and compositions should change over time. These models are powerful, but they are still models. They depend on physics such as nuclear fusion, convection, opacity, and energy transport inside stars. Small uncertainties in those details can become significant when dealing with extremely old objects. This is why ancient stars usually do not prove that the universe is older. They are better understood as stress tests. A stress test does not automatically break something. It applies pressure to see how well the structure holds. If old stars consistently appeared older than the universe, that would be a major crisis for cosmology. But when distance, composition, brightness, and stellar models are treated carefully, ancient stars and globular clusters generally fit within the standard age of the universe. Still, they remain deeply important. They give scientists an independent way to check the cosmic timeline. The age of the universe inferred from the cosmic microwave background and expansion history should not conflict with the ages of the older stars. The two methods are very different, which makes their agreement meaningful. One reads ancient radiation from the early universe. The other studies long-lived stars still glowing in galaxies today. When both point toward a consistent story, confidence grows. Ancient stars also remind us that the universe did not wait long before beginning its creative work. The first stars must have formed from simple gas, mostly hydrogen and helium. Later generations inherited heavier elements produced by earlier stars. Over billions of years, this process built the chemical richness needed for rocky planets, oceans, atmospheres, and biology. In that sense, the oldest stars are not just cosmic fossils. They are evidence of the first steps in the long chain that eventually made familiar matter possible. So the oldest stars do not overthrow the age of the universe, they quietly test it. They ask whether the timeline has enough room for them to form, shine, and survive. So far the answer appears to be yes, though sometimes only after careful revision and a little scientific sweating. The universe's age remains strongly supported, but ancient stars keep the number honest. They sit near the edge of the timeline, glowing faintly, reminding us that a good measurement must make room not only for the beginning of everything, but for the oldest survivors still carrying that beginning in their light. The oldest stars give scientists a way to test the universe's timeline from inside galaxies, but recently another kind of evidence has made the early universe feel even more intriguing. It comes not from ancient stars still shining nearby, but from galaxies so distant that their light began travelling when the cosmos was still very young. To see that far back, astronomers needed a telescope built almost like a time machine. That telescope is the James Webb Space Telescope. The James Webb Space Telescope is one of the most important observatories ever sent into space. It is a partnership between NASA, the European Space Agency, and the Canadian Space Agency, and it was designed to study the universe mainly in infrared light. That matters because the earliest galaxies are not easy to see in ordinary visible light. As their light travels across the expanding universe, space stretches the wavelengths. Light that may have started as ultraviolet or visible radiation can arrive at Earth shifted into the infrared. Webb was built to detect that stretched ancient light, making it especially powerful for looking into the deep past. This is one of the stranger gifts of cosmic expansion. The farther a galaxy is, the longer its light has usually been travelling, and the more that light has been stretched by the expansion of space. So when Webb looks at extremely distant galaxies, it is not only seeing far away, it is seeing long ago. Some of the galaxies it observes appear as they were only a few 100 million years after the Big Bang. That is early enough that the universe had not yet settled into the grand familiar appearance of spiral galaxies, galaxy clusters, and mature cosmic structures. It was still, in a sense, getting its furniture arranged. Before Webb began sending back data, Many scientists expected the earliest galaxies to be small, faint, irregular, and still in the early stages of assembly. That expectation made sense. Gravity needs time to pull gas into dense regions. Stars need time to form. Galaxies need time to grow through mergers, star formation, and the gathering of matter inside dark matter halos. The young universe was dense and energetic, but it was also young. There had simply not been much time, at least by cosmic standards, for large and developed galaxies to appear. Then Webb began looking. Some of the early galaxies it found seemed surprisingly bright. Some appeared more massive than expected. Some looked as if they already contained large numbers of stars. Others showed signs of chemical enrichment, suggesting earlier generations of stars had already lived and died. These observations did not mean that cosmology had suddenly collapsed into a small pile of equations and embarrassment. But they did make astronomers pause. The early universe seemed to have been busier than expected, like a bakery that somehow produced an entire wedding cake shortly after opening the doors. One of Webb's major deep field programs is the JADE survey, which stands for the James Webb Advanced Deep Extragalactic Survey. This project uses Webb's instruments to study extremely distant galaxies in some of the most carefully observed regions of the sky. Deep field surveys are valuable because they stare into small patches of space for long periods, gathering faint light from objects so remote that they would otherwise remain invisible. In those tiny windows, astronomers can find galaxies from some of the earliest chapters of cosmic history. Among these distant objects is JADE's GSZ 13.1, often written in a more compact scientific form, but best spoken as JADE's GSZ 13.1. This galaxy is observed as it was roughly 330 million years after the Big Bang. That may sound like a long time in human terms, because it absolutely is. 330 million years is older than the first dinosaurs by a comfortable margin. But for the universe, it is very early. Compared with an age of about 13.8 billion years, this is near the cosmic dawn, when the first galaxies were beginning to light up the darkness. A galaxy observed at that early time matters because it gives scientists a direct test of how quickly structure formed. By studying its light, astronomers can estimate properties such as redshift, brightness, star formation, and sometimes chemical signatures. These details help reveal what the galaxy was like when the universe was only a small fraction of its current age. If many galaxies from that era are brighter, more numerous, or more developed than predicted, then scientists must ask whether early galaxy formation was more efficient than their models assumed. There are several possible explanations. Early galaxies may have formed stars very rapidly because gas was denser in the young universe. Dark matter halos may have gathered material quickly, creating conditions where star formation could ignite with surprising efficiency. Some galaxies may look brighter because they contain intense bursts of young, massive stars. Others may appear more massive at first glance than they truly are, because estimating mass from ancient light is difficult and depends on assumptions about stellar populations, dust, and star formation history. The universe is not always lying exactly, but it can be annoyingly subtle. This is why careful framing matters. Webb has not simply broken cosmology. That phrase is dramatic, and dramatic phrases do tend to travel faster than cautious ones, especially on the internet where nuance often wears slippers and moves slowly. The standard model of cosmology remains very successful. The cosmic microwave background still strongly supports an age of about 13.8 billion years. The large-scale structure of the universe still broadly fits the lambda cold dark matter model. Webb's discoveries are not a simple announcement that everything scientists believed was wrong. What Webb has shown is more interesting than that. It has revealed that the early universe may have been capable of building galaxies faster, more efficiently, or in more varied ways than many models expected. The first few 100 million years may have been a more active period than previously imagined. Star formation may have switched on vigorously in some regions. Galaxies may have assembled rapidly inside dense early environments. Black holes may have begun growing sooner. Dust and heavy elements may have appeared earlier than once seemed likely. This connects directly to the question of whether the universe may be older than we think, but in a careful way. The Webb observations do not prove that the universe has more years behind it. Instead, they make some parts of the early universe look older in development. A galaxy only a few 100 million years after the Big Bang may appear surprisingly mature, not because it is secretly ancient, but because growth in the young universe may have happened quickly. The issue may be less about adding time to the cosmic clock and more about understanding how much could happen inside the time already available. In that sense, Webb has made the universe feel stranger without making it less scientific. It has not taken away the 13.8 billion year estimate. It has placed new pressure on the story around that estimate. If galaxies were already shining brightly at 330 million years, then the first stars and structures must have formed even earlier. If early galaxies were more massive or more chemically developed than expected, then the first chapters of cosmic history were rich with activity. The James Webb Space Telescope has opened a deeper window into the young universe, and through that window the cosmos does not look simple. It looks energetic, crowded, surprising, and wonderfully inconvenient. The ancient light arriving in Webb's mirrors is not telling scientists to abandon everything they know. It is asking them to look more carefully at how quickly darkness gave way to structure, and how much history may have been packed into the universe's first quiet dawn. Some of the most intriguing galaxies found in the early universe are not surprising merely because they exist. The universe was expected to form galaxies early. Gravity is very good at pulling matter together, given enough time, and it does not seem to mind working in the dark. The surprise comes from how developed some of these galaxies appear to be. They do not always look like simple, chaotic clouds just beginning to gather themselves. Some appear bright, massive, chemically enriched, dusty, or even structurally organized at times when the universe was still very young. That creates a timing problem, not necessarily a crisis, but a genuine scientific puzzle. Galaxies are not assembled instantly. A mature galaxy is not just a bright patch of stars. It is a system with gas, dust, star formation, dark matter, heavy elements, and often a central black hole. Many galaxies also develop recognizable shapes, such as disks, spiral arms, or bars. Each of these features requires physical processes that take time. Gas must fall into dark matter halos. Stars must form from collapsing clouds. The first generations of stars must live and die before they can enrich their surroundings with heavier elements. Dust must form from those elements. Structures must settle, rotate, merge, and reorganize. So when astronomers find galaxies that seem unusually developed only a few 100 million years after the Big Bang, the question becomes quiet but persistent. How did they grow up so quickly? The first thing to say is that surprising does not mean impossible. A surprising galaxy is not a cosmic rule breaker simply because it formed earlier than expected. It may be showing scientists that the early universe was better at building structure than many models had assumed. Models are not guesses, but they are simplified representations of complicated reality. They include gravity, gas physics, dark matter, radiation, star formation, and feedback from stars and black holes. But the early universe was a difficult place to simulate perfectly. It was dense, hot, dynamic, and full of conditions that cannot be recreated in a laboratory unless someone has a spare young universe, which currently remains a funding challenge. One possible explanation is that early galaxies formed stars more efficiently than expected. In the young universe, gas was more abundant and more tightly packed into smaller regions. Dark matter halos may have gathered gas quickly, creating deep gravitational wells where matter could collapse and ignite star formation. If the gas cooled effectively in certain regions, it could form stars at a rapid pace. Massive young stars are extremely bright, so even a relatively small galaxy could appear surprisingly luminous if it was going through an intense burst of star formation. Another possibility is that some early galaxies are being interpreted through light that is difficult to untangle. When astronomers estimate a galaxy's stellar mass, age, or maturity, they are not weighing it on a cosmic scale. They are reading its light. That light may come from many different kinds of stars mixed with dust, gas, and sometimes emission from an active central black hole. A galaxy can look massive because it has many stars, or because it contains a population of especially bright young stars. It can look red because it is old, dusty, distant, or some mixture of all three. The universe, once again, is not always being deliberately awkward, but it does enjoy making astronomers work for their conclusions. Dust is especially important. Dust in galaxies is made from heavier elements, such as carbon, oxygen, silicon, and iron, which are created inside stars and spread through space by stellar winds and supernova explosions. Finding dust in an early galaxy means that stars had already formed, evolved, and returned processed material to their surroundings. That takes time. Dust also changes how galaxies look because it absorbs and re-emits light. To study dust and cold gas in distant galaxies, astronomers use observatories such as the Atacama Large Millimeter Submillimeter Array in Chile. This array of radio telescopes observes light at long wavelengths, making it extremely valuable for studying cool gas, dust, and star formation in galaxies whose visible light has been stretched by cosmic expansion. The Atacama Large Millimeter Submillimeter Array works alongside telescopes such as the James Webb Space Telescope. Webb is excellent at detecting infrared light from ancient stars and galaxies. The Atacama Array can reveal the hidden reservoirs of gas and dust that help galaxies grow. Together, these observatories give a more complete view. One telescope may show the starlight, another may show the cold material from which stars are forming. It is rather like trying to understand a bakery by looking not only at the cakes in the window, but also at the flour, ovens, and the person at the back wondering why the early universe has placed such a large order. Some of the most eye-catching discoveries involve early galaxies that appear more organized than expected. Astronomers have found distant systems with disk-like structures, and Webb has revealed galaxies from early cosmic times that appear to contain bars. A bar is an elongated structure of stars running through the central region of some disk galaxies, including the Milky Way. Bars are important because they can help move gas inward, influence star formation, and shape how a galaxy evolves. For a long time, many astronomers thought strong bars would be more common in later settled galaxies because disks need time to become stable enough for such structures to form. Finding massive barred spiral systems at earlier times does not mean the universe is definitely older. It means that galaxy organization may have happened earlier, faster, or through more varied pathways than expected. Some early galaxies may have formed rotating disks quickly because gas flowed into them in steady streams. Others may have been shaped by mergers, gravitational interactions, or dense environments. A young galaxy does not have to be calm in order to become structured. Sometimes, structure emerges from turbulence, which is a comforting thought if one has ever looked at a messy desk and hoped it was actually an early stage of organization. Central black holes add another layer to the timing problem. Many mature galaxies contain massive black holes in their centers. If early galaxies already hosted growing central black holes, then those black holes also needed time to form and feed. They may have started from the collapsed remnants of very massive first stars, or from direct collapse events where huge clouds of gas formed black holes without first making ordinary stars. Either way, early black holes can make young galaxies appear more energetic and complicated. All of this connects back to the deeper question of age. These galaxies can make the universe look older in a developmental sense, even if the clock age remains close to 13.8 billion years. A child who can read, cook, and file tax documents at the age of 3 would not necessarily be secretly 80 years old, but someone would be right to ask what unusual conditions produce such alarming competence. Early mature galaxies create a similar feeling. They may not add years to the universe, but they compress more activity into the years already available. The most careful interpretation is that the young universe may have been more efficient than once assumed. Dense gas, rapid cooling, early dark matter structures, intense star formation, and fast chemical enrichment could have helped some galaxies develop quickly. Observations from Webb and the Atacama Large Millimeter-Submillimeter Array are not simply breaking old ideas, they are sharpening them. They show that the first galaxies were not all faint, slow, and simple. Some were already building stars, dust, structure, and perhaps central black holes with remarkable speed. So the mystery is not only how old the universe is, it is also how much the universe managed to do while it was still young. The clock may still point close to the familiar age, but the contents of those early hours look richer than expected. And that may be one of the quietest ways the universe can surprise us, not by being older in years, but by being older in behavior, already busy, already bright, already beginning to organize itself while the cosmic dawn had barely opened its eyes. The early universe began with very simple ingredients. After the first few minutes, it contained mostly hydrogen and helium, with tiny traces of a few other light elements. There was no oxygen to breathe, no carbon to build living chemistry, no iron for planets to hide in their cores, and no calcium for bones, shells, or the deeply unreasonable idea of teeth. The universe was vast, hot, expanding, and almost chemically plain. That plainness matters because the galaxies seen by modern telescopes are not chemically plain. Even very distant galaxies can show signs of heavier elements, dust, and complex star formation. Those heavier elements are not supposed to appear from nowhere. They have to be made. In the universe, the great makers of heavier elements are stars, especially massive stars that live intensely, burn through their fuel, and return enriched material to space. The first generation of stars is known as population 3 stars. These stars are still hypothetical in the sense that astronomers have not yet directly confirmed an individual pristine population 3 star. But the idea is strongly grounded in cosmology. They would have formed from the original material left after the Big Bang, mostly hydrogen and helium, before heavier elements became common. Because their gas contained almost no heavy elements, it would have cooled and collapsed differently from later star-forming clouds. Many population 3 stars may have been extremely massive, far larger than the Sun, perhaps living brief and brilliant lives before ending violently. The name can sound a little backwards. Population 1 stars, like the Sun, are relatively rich in heavier elements. Population 2 stars are older and poorer in heavier elements. Population 3 stars are the oldest proposed category of all, made from the cleanest original cosmic material. It is a numbering system that behaves a bit like someone labelled a cupboard after already filling it, which is not ideal, but astronomy has survived worse. The process that changes the chemistry of the universe is called stellar nucleosynthesis. This is the creation of heavier atomic nuclei inside stars. In their cores, stars fuse lighter elements into heavier ones, releasing energy in the process. Hydrogen can fuse into helium. In later stages of massive stars, helium and heavier nuclei can be fused into elements such as carbon, oxygen, neon, magnesium, silicon, sulfur, and eventually iron. Iron is a kind of turning point, because fusing iron into heavier elements does not release energy in the same useful way. For many heavier elements beyond iron, more extreme processes are needed, including supernova explosions and neutron star mergers. Fred Hoyle was one of the major scientists who helped explain how stars manufacture elements. A landmark paper published in 1957 became known as the B2FH paper, named from the initials of Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. This work helped describe how many of the elements are built inside stars and during stellar explosions. It connected the chemistry of ordinary matter to the lives and deaths of stars. The atoms in planets, oceans, rocks, and bodies were not simply placed into the universe fully formed. They were cooked, scattered, recycled, and eventually gathered again. This chemical clock is important for understanding early galaxies. If a galaxy very far away already contains heavier elements, then stars must have existed there before the light we now observe left it. Those earlier stars had to form, live, produce heavier elements, and return those elements to surrounding gas. If dust is present, the story becomes even more interesting, because cosmic dust is made from heavier elements. Dust grains can form in the outflows of aging stars, in supernova debris, and in dense interstellar environments. Finding dust in a very early galaxy means the universe had already completed several steps in chemical development. Supernovae are especially powerful agents of enrichment. When massive stars reach the ends of their lives, their cores can collapse and their outer layers can be blasted into space. These explosions release newly formed elements into the surrounding gas, where they can mix into future generations of stars and planets. A supernova is not merely a star dying with theatrical confidence. It is also a delivery system, spreading the ingredients for later complexity across interstellar space. Stellar winds also play a role. Massive stars can lose material throughout their lives, pushing enriched gas into their surroundings before they explode. This material can shape nearby clouds, trigger or suppress star formation, and alter the chemical makeup of young galaxies. In dense early environments, where gas clouds were close together and star formation may have been intense, enrichment could have happened quickly. The first stars may have lived only a few million years, which is brief by cosmic standards, but long enough to change the chemistry of their surroundings. This helps explain why some young galaxies can appear unexpectedly developed. If early star formation happened in rapid bursts, then chemical enrichment could begin very early. A galaxy only a few 100 million years after the Big Bang might already contain the ashes of earlier stars. Its light might carry signs of oxygen, carbon, dust, and energetic star-forming regions. That does not necessarily mean the galaxy is older than the universe's standard timeline allows. It may mean the earlier stars worked quickly, burned fiercely, and left their fingerprints sooner than expected. Still, the timing matters. Heavy elements are like timestamps written into galactic light. They do not tell scientists only that a galaxy exists. They tell scientists that something happened before that galaxy reached the state being observed. A chemically enriched galaxy has a backstory. It has already passed through earlier star formation, stellar death, gas mixing, and renewed star birth. The more enrichment found at very early times, the more tightly packed the first chapters of cosmic history become. Cosmic age, then, is not only about expansion, it is also about whether enough time existed for complex structures to appear. The universe had to expand and cool. Gas had to gather. The first stars had to ignite. Those stars had to create heavier elements. Some had to explode or shed material. New stars and galaxies then had to form from enriched gas. Each stage takes time, even if some stages can happen quickly under the right conditions. This is why the chemical evidence from early galaxies is so valuable. It does not overturn the age of the universe by itself. It does not prove that 13.8 billion years is wrong. Instead, it tests how much activity can fit into the early timeline. If young galaxies already contain heavy elements and dust, scientists must understand how the first stars formed, how massive they were, how quickly they died, and how efficiently their material spread. The first stars are gone, or nearly impossible to see directly, but their influence remains. They change the universe from a simple mixture of hydrogen and helium into a place capable of chemistry, planets, and eventually life. In that sense, the chemical clock is one of the most intimate clocks in cosmology. It measures not just how long the universe has existed, but how quickly it learned to make the ingredients of everything familiar. After the cosmic microwave background was released, the universe entered one of its quietest and most mysterious periods. Space had become transparent to that ancient background light, but the first stars and galaxies had not yet filled the darkness with their own strong radiation. There were atoms, mostly hydrogen and helium. There was dark matter pulling matter into growing structures. There were tiny density differences slowly becoming more important under gravity. But there were not yet familiar constellations, glowing galaxies, or the bright architecture of the later cosmos. This period is known as the Cosmic Dark Ages. The name sounds dramatic, but it simply means there were no stars shining through space in the way they would later. The universe was not empty. It was expanding, cooling, and quietly preparing the conditions for structure. Neutral hydrogen gas filled much of space, and gravity was gathering matter into denser regions. In those regions, the first stars would eventually ignite, and the first galaxies would begin to take shape. For a while, though, the universe was like a stage after the curtain had risen, but before the lights had come on. Then the first sources of strong light appeared. The earliest stars, the first galaxies, and possibly growing black holes began producing ultraviolet radiation. This ultraviolet light had enough energy to alter the neutral hydrogen gas around it. A neutral hydrogen atom contains one proton and one electron bound together. When energetic ultraviolet light strikes it, the electron can be knocked away. This process is called ionization. When it happened across huge regions of the young universe, scientists call the period the epoch of reionization. The word reionization may sound as though the universe was repeating itself, and in a way it was. In the very early universe, matter had once been ionized because it was extremely hot. Electrons and nuclei moved separately in a dense plasma, and light could not travel freely for long. Then the universe cooled, neutral atoms formed, and the cosmic microwave background was released. Later, after the first stars and galaxies switched on, their ultraviolet light ionized much of that neutral hydrogen again. The universe moved from a foggy neutral state into a more transparent ionized one. This process did not happen everywhere at once. It was probably patchy and uneven. Around the first bright galaxies, ultraviolet light carved bubbles in the surrounding hydrogen gas. These bubbles grew as more stars formed and more radiation escaped. Over time, neighbouring bubbles overlapped, until much of the space between galaxies was ionized. It was not a single cosmic light switch being flicked. It was more like lanterns slowly appearing across a misty landscape, each one clearing a small region until the mist finally began to thin. Quasars are important tools for studying this transformation. A quasar is an extremely bright active galactic nucleus powered by a supermassive black hole feeding on surrounding material. Because quasars can be seen across enormous distances, their light passes through intervening hydrogen gas on its way to Earth. That gas leaves absorption features in the quasar's spectrum. giving astronomers clues about how neutral or ionized the universe was at different times. One key clue is called Gunn-Peterson absorption, named after James Gunn and Bruce Peterson. It refers to the way neutral hydrogen absorbs light at specific wavelengths, especially light connected to hydrogen's Lyman alpha transition. When scientists study the spectra of very distant quasars, strong Gunn-Peterson absorption can reveal that large amounts of neutral hydrogen still existed along the line of sight. By comparing quasars at different redshifts, astronomers can trace the end of the cosmic fog and estimate when reionization was largely complete. The James Webb Space Telescope has added a new level of detail to this story. Webb can observe very distant early galaxies whose light has been stretched into infrared wavelengths by cosmic expansion. Some of these galaxies show bright hydrogen emission, suggesting intense star formation and energetic radiation. In certain cases, astronomers have considered whether young galaxies may have cleared surprisingly large bubbles in the surrounding neutral hydrogen earlier than expected. That matters because bright hydrogen emission should be harder to see if a galaxy is still buried inside thick neutral gas. If the emission escapes clearly, it may mean the galaxy has already carved out a transparent region around itself. This is where the timing becomes important. If galaxies only a few 100 million years after the Big Bang had already cleared large bubbles in the cosmic fog, then those galaxies must have been producing strong radiation efficiently. Their stars may have formed rapidly. Their ultraviolet light may have escaped more easily than expected. Their black holes, if present, may have helped ionize nearby gas, or the surrounding environment may have been unusually favorable, with clustered galaxies working together to clear larger regions. None of this proves that the universe is older than the standard estimate, but it can make parts of the early universe look developmentally advanced. Reionization is not just a lighting change. It is a major physical transformation of the universe's gas. It requires sources of energy, enough time for those sources to form, and enough radiation to spread through vast regions of space. If this transformation began earlier or progressed faster than expected, scientists have to ask whether the first stars and galaxies formed unusually quickly, whether radiation escaped from them more efficiently, or whether the models are missing some important detail. The epoch of reionization therefore sits at the boundary between darkness and structure. It links the first stars, the earliest galaxies, the growth of black holes, and the changing transparency of space itself. It also reminds us that the age of the universe is not only a question of counting backward from today. It is a question of whether the sequence of events fits inside the available time. The universe had to cool, form atoms, gather gas, ignite stars, build galaxies, and then flood the darkness with enough ultraviolet light to transform the spaces between them. The cosmic fog did eventually lift. The universe became transparent not only to the ancient afterglow of the Big Bang, but to the starlight of galaxies spreading across deep time. Yet the details of that clearing remain one of the most active frontiers in cosmology. Somewhere in that misty era, the first lights began changing everything. And if those lights appeared earlier, brighter, or more forcefully than expected, then the early universe may once again be telling scientists that its first chapters were fuller, faster, and more quietly astonishing than the simplest timeline suggests. Some of the most difficult objects to fit neatly into the early cosmic timeline are not galaxies themselves, but the dark engines hidden inside some of them. These are supermassive black holes, the enormous black holes found in the centers of many large galaxies. In the modern universe, they can contain millions or even billions of times the mass of the Sun. The Milky Way has one called Sagittarius A star, sitting quietly at its center, though quietly is a relative word when discussing something with 4 million solar masses and no manners at the dinner table. The puzzle becomes sharper when astronomers find supermassive black holes in the early universe. Some appear as quasars, which are among the brightest objects in the cosmos. A quasar is not bright because the black hole itself shines. A black hole, by definition, is a region where gravity is so strong that not even light can escape once it passes the event horizon. The brightness comes from material outside the black hole. Gas and dust spiral inward, forming a hot accretion disk. As this material heats through friction and gravitational energy, it can glow with astonishing intensity, sometimes outshining the entire galaxy around it. Quasars can be seen across enormous distances, which means they can reveal black holes from very early cosmic times. Some quasars are observed as they were when the universe was less than 1 billion years old. That sounds ancient from a human point of view, but for building a black hole with hundreds of millions or billions of solar masses, it is not much time. A black hole has to begin somewhere, then grow by swallowing matter and merging with other black holes. Growth takes time, and there are limits to how quickly feeding can happen. The main difficulty is that a black hole cannot simply eat everything nearby without consequences. As gas falls toward it, the gas heats up and produces radiation. That radiation pushes outward on surrounding material. If the inflowing gas becomes too bright, the outward pressure from radiation can slow or even halt further accretion. The important concept here is called Eddington luminosity, named after the British astrophysicist Arthur Eddington. Eddington luminosity is the brightness at which the outward force from radiation balances the inward pull of gravity on infalling material. It acts like a kind of cosmic speed limit for steady black hole feeding. This does not mean black holes can never grow quickly. It means that ordinary continuous growth has constraints. If a small black hole begins as the remnant of a massive star, perhaps with tens or hundreds of times the mass of the Sun, it has to grow enormously to become 1 billion solar mass black hole. It must feed efficiently and steadily for a long time, or it must start from a much larger seed, or it must experience periods of unusually rapid accretion. Otherwise, the timeline becomes uncomfortable. One possible solution is that the first black hole seeds were much larger than the remnants of ordinary stars. Direct collapse black holes are one proposed route. In this scenario, a huge cloud of gas in the early universe collapses almost directly into a black hole, without first breaking apart into many normal stars. This could create a black hole seed with tens of thousands, or perhaps hundreds of thousands of solar masses. Starting with a larger seed makes it easier to reach supermassive size by early cosmic times. It is the difference between growing an oak from an acorn and beginning with a suspiciously large sapling that has clearly had help. Another possibility involves unusually massive first stars. Population 3 stars, the hypothesized first generation of stars, may have formed from nearly pristine hydrogen and helium gas. Because this gas lacked heavier elements, it cooled differently from later star-forming gas. Some population 3 stars may have become extremely massive. When such stars died, they could have left behind black holes larger than those typically produced by ordinary stars today. These remnants would still need to grow rapidly, but they might provide a better starting point. Rapid accretion episodes may also help. The Eddington luminosity applies to steady, spherical, idealized feeding, but real astrophysical environments can be messy. Gas may fall in unevenly. Accretion disks may be thick, clumpy, or structured in ways that allow some radiation to escape without stopping all incoming material. In certain conditions, black holes may briefly grow faster than the standard Eddington rate. These super Eddington accretion episodes are an area of active study. They offer a way for young black holes to gain mass quickly, though they require the right supply of gas and the right physical conditions. Dense early environments could make the problem easier too. The young universe was more compact than it is today, and matter was more tightly packed on, average. Early galaxies and proto-galaxies may have contained thick reservoirs of gas. Frequent mergers could have brought black holes together, adding mass through collisions. gas-rich surroundings could have fed central black holes intensely. If the earliest galaxies were crowded nurseries of stars, gas and dark matter, then black holes may have found more generous feeding grounds than they usually do today. Still, the puzzle remains important because black holes act as another kind of cosmic growth clock. Their size tells a story. A billion solar mass black hole in the early universe implies earlier formation, rapid feeding, large initial seeds, repeated mergers, or some combination of these. If black holes appear too massive too soon, scientists must ask which part of the story needs adjusting. Was there more time available than the standard timeline suggests? Did black holes grow faster than expected? Were their starting conditions much more extreme? Or do models of early black hole formation need refinement? This connects directly to the question of whether the universe may be older than we think. Early supermassive black holes do not prove that it is. They do not overturn the cosmic microwave background or erase the standard age of about 13.8 billion years. But they do add pressure to the early timeline. Like mature-looking galaxies, they suggest that some cosmic structures reached impressive sizes very quickly. The universe may not need extra years, but it may have used its earliest years far more efficiently than once assumed. The most careful view is that early black holes are signposts of intense cosmic growth. They reveal that the first galaxies were not quiet, simple places. They were energetic environments where gas collapsed, stars formed, black holes fed, and radiation poured into surrounding space. Quasars from the early universe are therefore not just bright objects. They are evidence of enormous engines already running when the cosmos was young. Their existence makes the age question richer. The issue is not simply whether the clock should be reset. It is whether the processes inside the early universe were faster, heavier, denser, and more extreme than expected. A black hole that seems too massive too soon may not be telling scientists the universe is older. It may be telling them that the first chapters of cosmic growth were written with unusual speed, in ink so dark and bright that it can still be seen from billions of years away. The universe's age depends on expansion, but expansion is not a simple motion that has stayed the same forever. It has changed over time. In the earliest eras, radiation was important. Later, matter and dark matter shaped the slowing of expansion through gravity. More recently, something else has become dominant. Something that appears to push the universe into accelerating expansion. Scientists call it dark energy. Dark energy is not a substance that has been collected, bottled, labelled and placed gently on a laboratory shelf. The name is more cautious than that. It is the name given to whatever is causing the accelerated expansion of the universe. Observations show that distant galaxies are not merely moving away from one another because of earlier expansion. On the larger scales, the expansion of space appears to be speeding up. Something seems to act against the attractive pull of gravity across cosmic distances, and dark energy is the placeholder name for that unknown cause. This discovery came from studies of distant Type 1a supernovae in the late 20th century. These exploding stars can be used as standardizable candles, meaning their changing brightness allows astronomers to estimate their distances. Saul Perlmutter, Brian Schmidt, Adam Rees, and their teams found that distant supernovae were dimmer than expected. The most natural explanation was that the expansion of the universe had accelerated over time, stretching space more than a steadily slowing universe would have done. It was a deeply surprising result, the sort of discovery that makes the universe seem polite for billions of years and then suddenly admit it has been doing something very odd in the background. Within the standard model of cosmology, the simplest explanation for dark energy is the cosmological constant. This idea has a long and slightly awkward history. Albert Einstein introduced the cosmological constant into his equations of general relativity in the early 20th century, when many scientists still believed the universe was static. Its original purpose was to help hold the universe still against gravitational collapse. After observations showed that the universe is expanding, Einstein reportedly came to regret the term, although the famous story of his biggest blunder is not as tidy as it is often told. Later, after the discovery of accelerated expansion, the cosmological constant returned in a new role. In modern cosmology, the cosmological constant can be understood as a constant energy associated with space itself. Unlike matter, which becomes more diluted as space expands, this form of energy density remains constant in each volume of space. As the universe expands and matter thins out, the influence of dark energy becomes more important. Eventually it begins to dominate the large-scale behavior of the cosmos, causing expansion to accelerate. This is the lambda part of the lambda cold dark matter model, with lambda referring to the cosmological constant. But calling it a cosmological constant does not mean scientists truly understand what it is. It is a successful description, not a complete explanation. The observed value is extraordinarily small compared with some expectations from quantum field theory, creating one of the deepest unsolved problems in physics. Dark energy behaves, observationally, like a smooth energy of empty space, but whether it is truly constant, connected to vacuum energy, caused by a new field, or signaling a deeper modification of gravity remains unknown. This matters for the age of the universe because cosmic age is calculated from the whole expansion history, not just the expansion rate today. Imagine trying to work out how long a journey took by knowing only the current speed of a car. That information helps, but it is not enough. The car may have slowed down, sped up, stopped for snacks, or taken a mysterious detour through dark energy, which would at least explain some of the confusion. In cosmology, scientists need to know how expansion changed across billions of years. Several ingredients shape that history. Radiation dominated the very early universe, when light and fast-moving particles had a much stronger influence. Matter, including ordinary matter and dark matter, later became more important. Matter pulls through gravity, slowing expansion compared with what it would otherwise do. Dark matter is especially important because it provides much of the gravitational structure that allows galaxies and galaxy clusters to form. Curvature also matters because the overall geometry of space affects how expansion behaves. Though current observations suggest the universe is very close to flat on large scales. Then dark energy becomes dominant in the later universe, pushing expansion into acceleration. The balance between these ingredients determines how long the universe takes to evolve from its hot, dense early state to its current condition. If matter were more dominant, expansion would have slowed differently. If dark energy became important earlier or later, the timeline would shift. If the universe had significant curvature, the age calculation would also change. The familiar estimate of about 13.8 billion years depends on fitting all these ingredients together in a model that matches observations such as the cosmic microwave background, galaxy clustering, supernova distances, and the present-day expansion rate. The key question is whether dark energy has always behaved like a true cosmological constant. If its strength has remained unchanged over time, the standard model gives a very consistent cosmic history. But if dark energy changes with time, then the expansion history could be different. A stronger influence in the past, a weaker influence in the past, or some evolving behavior could alter how quickly the universe expanded at different eras. Even a subtle change could affect the inferred age, because the age is the total result of expansion across the entire observable history of the universe. This is one reason scientists study distant supernovae, baryon acoustic oscillations, gravitational lensing, and galaxy surveys so carefully. They're trying to map expansion not just now, but across time. The Dark Energy Survey, the Dark Energy Spectroscopic Instrument, the European Space Agency's Euclid mission, and the Vera C. Rubin Observatory all contribute to this larger effort. Each helps test whether dark energy behaves exactly like a cosmological constant, or whether the universe has a more complicated expansion story. So the age of the universe is not simply a stopwatch reading. It is a reconstruction of changing expansion, shaped by radiation, matter, dark matter, curvature, and dark energy. If any of those ingredients behaves differently from what the standard model assumes, the timeline may need adjustment. The universe may still be close to 13.8 billion years old, but the route to that age could become stranger and more subtle. Dark energy therefore gives the question a deeper shape. The universe may not be older because one number was misread. If the age changes, it may be because the expansion of time and space has followed a path more complex than expected. To understand how old the universe is, scientists must understand not only where it is now, but how its expansion has breathed, slowed, stretched, and accelerated across the long, dark river of cosmic time. One possible response to the puzzles in modern cosmology is to ask whether the early universe contained something extra. Not extra in the sense of a misplaced galaxy or a forgotten box of spare atoms left over from creation, but an additional ingredient in the equations that shaped expansion when the universe was very young. One of the most discussed versions of this idea is called early dark energy. Early dark energy is a proposed form of energy that would have briefly influenced the expansion of the young universe before fading away or becoming unimportant. It is not the same as the dark energy that appears to dominate the universe today, though the name is naturally related. Today's dark energy is used to describe the mysterious cause of the universe's accelerated expansion in recent cosmic history. Early dark energy, by contrast, would have played a temporary role much closer to the beginning, leaving subtle traces in the cosmic microwave background and the later growth of structure. The reason this idea has received attention is the Hubble tension. Measurements based on the cosmic microwave background interpreted through the lambda cold dark matter model tend to give a lower present-day expansion rate than measurements based on the local distance ladder. One way to ease this tension is to adjust what the early universe was doing. If an extra energy component briefly affected the universe before the cosmic microwave background was released, it could change the inferred size of key early universe features. That, in turn, could shift the expansion rate predicted for the modern universe. The basic idea is delicate. The cosmic microwave background preserves a record of sound waves moving through the hot early plasma. These ancient patterns help set a kind of standard ruler for cosmology. If early dark energy briefly changed how the universe expanded before those patterns were frozen into the microwave background, it could alter the ruler. A changed ruler could lead scientists to infer a different present-day expansion rate, potentially bringing early universe and local measurements closer together. This is not a simple case of adding one mysterious ingredient and making all the problems vanish, because the universe has a habit of checking the paperwork. Mark Kamionkowski is one of the researchers associated with influential work on early dark energy as a possible response to the Hubble tension. Vivian Poulin has also been closely associated with important early dark energy models and studies, especially those exploring whether a temporary energy component before recombination could raise the expansion rate inferred from early universe data. These researchers and others have examined how such models might work, what they could explain, and where they create new difficulties. That last part is crucial. Early dark energy is not confirmed. It is a serious proposal, not an established discovery. Cosmology is tightly constrained because many observations have to fit together at once. A model cannot merely improve the Hubble tension and then stroll away looking pleased with itself. It must also match the cosmic microwave background in detail. It must agree with galaxy surveys. It must fit observations of supernovae, baryon acoustic oscillations, gravitational lensing, and the large-scale structure of the universe. It must not disturb successful predictions elsewhere beyond what the data allow. This is one of the quiet challenges of new physics. A new idea can solve one problem while creating pressure somewhere else. Early dark energy may help with the difference between early universe and local measurements of the Hubble constant, but it can also affect how matter clumps, how galaxies form, and how the cosmic microwave background patterns appear. If it changes expansion too much, too long, or at the wrong time, it may no longer fit the rest of the evidence. The universe is not a single lock with one key. It is more like an enormous, ancient instrument, and tuning one string can make another hum unexpectedly. Other new ideas have also been explored. Some involve additional light particles in the early universe. Some consider changes to dark matter, interactions between dark matter and dark energy, or modifications to gravity on cosmic scales. Others examine whether unknown systematic errors still exist in the measurements themselves. Each possibility has to be treated carefully because the standard lambda-cold dark matter model is not weak. It has succeeded across a remarkable range of evidence. Any replacement or extension must do at least as well, while also explaining what the standard model struggles with. This is why the phrase older than we think becomes more subtle. It may not mean simply adding more years to the universe, as if the cosmic calendar needs a few extra pages. It may mean rethinking how the earliest expansion unfolded. A change in the first few 100,000 years could alter how scientists interpret the later universe without necessarily turning 13.8 billion years into a dramatically different number. The story could change in shape more than in length. Early dark energy also shows how age, expansion, and model assumptions are intertwined. The age of the universe is not measured by one observation alone. It is inferred from a network of evidence interpreted through theory. If the theory changes, the meaning of the evidence can shift. The cosmic microwave background remains real. Galaxy distances remain real. Supernova measurements remain real. But the route connecting them into one timeline may become more complex. That does not weaken science. It is how science becomes more precise. When observations disagree in a persistent way, researchers do not have to immediately abandon everything, nor do they have to ignore the disagreement. They build new models, test them against the full range of evidence, and see which ones survive. Most ideas do not. Some survive longer than expected. A few eventually become part of the standard picture. The universe offers the data, and scientists try not to take it personally. Early dark energy remains an open possibility, not a settled answer. It is one of several attempts to understand whether the early universe contained ingredients or behaviors not captured by the simplest model. If such an ingredient existed, then the universe's first chapters may have been more complicated than the clean standard timeline suggests. The mystery may not be that the universe is secretly much older. It may be that, while still young, it expanded under rules whose full details are only beginning to come into view. The phrase "the Big Bang" can sound like the absolute beginning of everything. It has a satisfying simplicity to it, almost like the universe once rang a starting bell and all of space politely began. But in modern cosmology, the Big Bang is usually treated more carefully. It describes the early, hot, dense, expanding phase of the observable universe, the phase that can be studied through evidence such as cosmic expansion, the cosmic microwave background, and the abundance of light elements like hydrogen and helium. That distinction matters. The Big Bang model is not simply a story about an explosion happening at one point in empty space. It is a model of space itself expanding from an earlier, hotter, denser condition. When scientists traced the universe backward, galaxies were closer together, matter was denser, temperatures were higher, and radiation was more energetic. Go far enough back, and the physics becomes extreme enough that ordinary intuition begins to lose its grip. The question then becomes difficult. Was that hot, dense state the absolute beginning of reality, or only the earliest phase that current science can describe with confidence? This is where caution is essential. The standard model of cosmology can describe the universe extremely well from a very early time onward, especially after the first fractions of a second, and with great confidence after the formation of the cosmic microwave background. But the exact beginning, if there was one, remains far harder to define. General relativity points toward a state of enormous density when traced backward, but general relativity is not expected to be complete under those conditions. At the smallest scales and highest energies, quantum physics must also matter. A full theory of quantum gravity would be needed to speak confidently about the deepest beginning, and no such theory has yet been confirmed. One important idea connected to the early universe is cosmic inflation. Inflation proposes that the universe underwent an incredibly rapid expansion during an extremely early moment. This idea was developed in important ways by Alan Guth, Andrei Linde, and Alexei Starobinsky. Inflation was introduced partly to explain several puzzling features of the observable universe. One is its large-scale smoothness. Regions of space very far apart have nearly the same temperature in the cosmic microwave background, even though they seem too distant to have exchanged signals in the ordinary Big Bang picture. Inflation offers a way to explain this by suggesting those regions were once close together before space expanded enormously. Inflation may also help explain why the universe appears so close to flat on large scales. In cosmology, flatness refers to the geometry of space, not to anything like a flat sheet floating through the void. A flat universe is one where parallel lines behave in the familiar way on cosmic scales. Inflation could stretch any earlier curvature until the observable universe looks almost perfectly flat, a little like zooming into a tiny patch on the surface of a huge sphere until it looks level. The universe, being the universe, apparently prefers making geometry sound like a bedtime puzzle. Inflation also provides a possible origin for the tiny density variations that later grew into galaxies and galaxy clusters. According to inflationary theory, quantum fluctuations in the very early universe could have been stretched to cosmic scales. These small variations then became the seeds of structure. The cosmic microwave background carries traces of those early irregularities, and their pattern broadly fits the inflationary idea. This is one reason inflation is taken seriously, even though the exact mechanism behind it remains uncertain. But inflation does not automatically prove that the universe existed before the Big Bang in a simple, everyday sense. It depends on how the phrase Big Bang is being used. Some people use it to mean the hot, dense, expanding phase after inflation. Others use it to include the earliest possible beginning of everything. If inflation happened before the hot Big Bang phase, then the observable universe may have a prehistory beyond the part normally described by the simplest Big Bang picture. But that does not mean there was definitely a long stretch of ordinary time before it. Time itself may have behaved differently under such extreme conditions, and language begins to creak a little under the pressure. There are also speculative but serious frameworks that ask whether the hot Big Bang was not the first event. Bouncing cosmology proposes that the universe may have emerged from a previous contracting phase. Instead of beginning from nothing, the cosmos might have shrunk, reached an extreme state, and then expanded again. Cyclic cosmology explores the possibility of repeated cosmic phases, where expansion and renewal occur in some deeper pattern. These ideas are not established facts, but they are attempts to think mathematically about what might lie beyond the earliest observable era. Roger Penrose has proposed a version of cyclic thinking called conformal cyclic cosmology. In this view, the remote future of one cosmic era might be connected in a subtle mathematical way to the beginning of another. It is a bold and controversial idea, and it should be treated cautiously. It is not part of the standard cosmological model, and the evidence for it remains debated. Still, it shows that serious physicists do sometimes consider possibilities in which the hot Big Bang is not the absolute first page of reality, but a boundary between phases. This is where the title takes on a deeper meaning. The universe may not be older than we think in the simple sense that the 13.8 billion year estimate is plainly wrong. That number refers to the age of the observable universe since the hot, dense, expanding phase described by the standard model. It is strongly supported by evidence, but if the hot Big Bang was not the absolute beginning, then there may be a deeper sense in which reality has a history before the history we can directly reconstruct. That possibility remains speculative. The evidence does not currently require a previous universe, a bounce, or an endless cycle. The safest scientific statement is that the observable universe has a well-supported age of about 13.8 billion years, while the question of what, if anything, preceded the hot Big Bang remains open. There may have been no before in any familiar sense. There may have been a phase that current theories only dimly suggest, or the word beginning may need to be handled with far more care than ordinary language allows. The Big Bang, then, is not less important because it may not answer everything. It is the earliest well-grounded chapter of the cosmic story. It marks the boundary where evidence becomes strong enough to build a detailed model. Beyond that boundary, physics becomes quieter, stranger, and less certain. The universe may be exactly as old as the standard model says in the measurable sense, while still leaving open the deeper question of whether the visible story began at the true beginning or only at the first moment the cosmos became readable to science. The observable universe is not necessarily the whole universe. It is the part of the universe from which light has had enough time to reach us since the hot Big Bang. That definition is simple, but its meaning is enormous. It means the visible cosmos is shaped not only by what exists, but by what has had time to send a signal across expanding space. Beyond that limit, there may be more galaxies, more clusters, more empty regions, and more cosmic web. They may be real, but their light has not reached us, and may never reach us, depending on how the universe continues to expand. This is one of the quietest limits in science. It is not a wall. It is not a glass dome around Earth. It is not a sign at the edge of space saying, "Nothing to see here," although that would be refreshingly direct. The observable universe is a horizon. It is the boundary of what can be seen from our location at this time, using light or any other signal that travels no faster than light. It is a limit created by time, distance, expansion, and the finite speed of information. The universe is about 13.8 billion years old, according to the standard cosmological model. So it might seem natural to imagine that the observable universe should have a radius of 13.8 billion light-years. After all, if light has been travelling for 13.8 billion years, surely the farthest visible light should come from 13.8 billion light-years away. This sounds reasonable, and it is also wrong in a wonderfully cosmological way. The observable universe has a radius of roughly 46 billion light-years. The reason is that space expanded while the light was travelling. A photon from the early universe may have spent almost the entire age of the cosmos crossing space toward us. But during that journey, the space between its source and Earth was stretching. The object or region that emitted the light is now much farther away than the simple light travel time would suggest. The light has travelled for billions of years, but the distance to where it came from has grown during that same journey. This is why cosmological distances can feel so slippery. A galaxy observed as it was more than 13 billion years ago is not now only 13 billion light-years away. The galaxy's light has been travelling across expanding space, and the galaxy's present distance, if it still exists in the same recognisable form, can be much greater. The universe is not a static room where light crosses from one wall to another. It is more like a room whose walls, floor, and every stretch of empty space are quietly growing while the light is still on its way. An inconvenient arrangement for simple diagrams, but a very elegant one for keeping cosmologists busy. The boundary of what we can observe is often connected to the particle horizon. The particle horizon marks the maximum distance from which particles of light or other signals could have reached us since the beginning of the hot Big Bang phase. It defines the edge of the observable universe in terms of causal contact. If something lies beyond that horizon, its light has not had enough time to arrive. It may exist, but it cannot yet be part of our evidence. There is also a cosmic horizon connected to the universe's continuing expansion. Because dark energy appears to be driving accelerated expansion, some regions of space may be moving away from us in such a way that light emitted from them now will never reach us, even given unlimited future time. This does not mean those galaxies are locally travelling through space faster than light in an ordinary sense. It means the space between us and them is expanding so that the distance grows too quickly for their future light ever to cross it. The universe can hide things not by covering them, but by stretching the path between here and there. This creates a strange situation. The observable universe is already immense, containing perhaps hundreds of billions of galaxies, each with enormous numbers of stars, yet it may still be only a small part of the whole. The entire universe could be much larger than the observable region. It might even be infinite, though that remains unknown. Current observations suggest that space is very close to flat on large scales, which is consistent with an extremely large or infinite universe. But it does not prove infinity. Infinity is a large claim, and science likes to check its shoes before stepping into it. A larger universe is not the same as an older universe. That distinction is important. If there are regions beyond the observable horizon, they are not necessarily older than our region. In the standard picture, they would be part of the same overall cosmic expansion, sharing the same broad history from the hot Big Bang, even though we cannot observe them directly. Size and age are related through expansion, but they are not identical. A universe can be vastly larger than what we see without requiring extra time before the beginning of the observable cosmic timeline. Still, the fact that our evidence comes from a limited window matters deeply. Every measurement of cosmic age is made from inside the observable universe. The cosmic microwave background comes from the surface of last scattering within our horizon. Galaxy surveys map the structures we can see. Supernovae, quasars, redshifts, gravitational lensing, and ancient stars all belong to the accessible cosmic region. Science builds its best model from the evidence available, and that evidence is extraordinary. But it's not a view from outside the whole of reality. There is no external platform where an observer can stand back, admire the entire universe, and say, with complete authority, yes, that is definitely all of it. This does not make cosmology weak. It makes it honest. Scientists can infer some things about the larger universe from the part we observe, especially if the laws of physics appear consistent and the observable universe looks broadly uniform on large scales. The cosmological principle, the assumption that the universe is roughly the same everywhere on sufficiently large scales, helps make such reasoning possible, but assumptions still have to be tested against evidence, and beyond the horizon, direct testing becomes impossible. So, what we think about the universe is shaped by where we are and what can reach us. Cosmic age is partly a story told from inside a horizon. The 13.8 billion year estimate may be the best measurement for the age of the observable universe since the hot Big Bang, but the observable universe is not guaranteed to be the whole stage. It is the part of the stage whose light has arrived. This makes the title more subtle. The universe may not be older simply because more universe exists beyond sight. But the boundary reminds us that every cosmic measurement is made from within limits. We are reading ancient light from inside the story, not outside it. The age of the universe is therefore both one of science's greatest achievements and one of its most humbling conclusions. A number drawn from a horizon, measured by beings who can see astonishingly far, but not infinitely far. Scientific disagreement can sound unsettling from the outside, especially when the subject is something as vast as the age of the universe. It may seem as though science should have one clean answer, placed neatly on the table, dusted occasionally and left alone. But in reality, disagreement is often where science becomes most useful. A tension between measurements is not automatically a failure. It is a sign that the evidence has become precise enough for small differences to matter. Cosmology is full of these careful disagreements. Some are temporary, some reveal hidden errors, some fade as instruments improve, others become stronger, stranger, and more interesting until they point toward a deeper change in understanding. This is not a weakness in the scientific method. It is the method doing exactly what it's supposed to do. Science does not protect a favourite answer from discomfort. It keeps checking whether the answer survives. The age of the universe is a perfect example. The familiar estimate of about 13.8 billion years is not floating alone. It sits inside a network of measurements, including the cosmic microwave background, the expansion rate of space, the distribution of galaxies, the brightness of supernovae, and the ages of the oldest stars. If all of these lines of evidence agree, confidence grows. If one or two begin to pull in a slightly different direction, scientists do not immediately panic and throw the universe into a filing cabinet marked too difficult. They ask what the disagreement is trying to reveal. Independent checks are essential because every method has its own possible weaknesses. The cosmic microwave background is one of the strongest tools in cosmology. It gives a detailed view of the early universe, especially through surveys such as those made by NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck mission. These surveys measure tiny temperature variations in ancient light, allowing scientists to infer the universe's composition, geometry, and age within the lambda cold dark matter model. But because this method depends on interpreting early universe light through a model, it must be checked against other kinds of evidence. Supernova surveys provide one such check. Type 1a supernovae can be used as standardizable candles, helping astronomers measure distances across enormous stretches of space. They revealed that the expansion of the universe is accelerating, one of the discoveries that made dark energy central to modern cosmology. By comparing supernova brightness and redshift, scientists can trace how expansion changed over time. This gives a different view of the same cosmic history, like checking the route of a long journey from another map. Galaxy clustering offers another kind of evidence. Galaxies are not scattered randomly through space. They gather into filaments, walls, clusters, and immense empty regions called voids, forming the cosmic web. This structure grew from tiny early density variations under the influence of gravity and dark matter. The way galaxies cluster today carries information about the early universe, the amount of matter present, and the history of expansion. If a cosmological model predicts one pattern of structure, but surveys find another, the model has to answer for itself, preferably without mumbling. Baryon acoustic oscillations are especially valuable. In the hot young universe, ordinary matter and radiation supported sound waves moving through the dense plasma. These waves left a preferred scale in the later distribution of galaxies. Scientists can use that scale as a standard ruler, measuring how cosmic distances have changed over time. Baryon acoustic oscillations therefore help connect the early universe to the later universe in a way that is independent of the distance ladder. They are ancient sound waves turned into a measuring stick, which is a very elegant way for the universe to reuse its old noise. Gravitational lensing adds another check. Massive objects such as galaxies and galaxy clusters bend the path of light from more distant objects. This bending is predicted by Albert Einstein's general theory of relativity. By studying it, astronomers can map the distribution of matter, including dark matter, and test how structure has grown across cosmic time. Weak gravitational lensing, where many tiny distortions are combined statistically, is especially useful for studying the large-scale universe. It reveals not only where visible galaxies are, but where the invisible mass must be. There is also a newer method known as gravitational wave standard sirens. When compact objects such as neutron, stars or black holes merge, they send ripples through space-time called gravitational waves. The shape of the gravitational wave signal can reveal distance in a way that does not rely on the traditional cosmic distance ladder. If scientists can also identify the host galaxy and its redshift, the event can help measure the expansion rate of the universe. The first famous neutron-star merger detected in gravitational waves and light, observed in 2017, showed how powerful this method could become. It was not yet enough to settle the Hubble tension, but it opened another independent path. Large modern surveys are designed to sharpen these checks. The Dark Energy Survey has mapped hundreds of millions of galaxies and studied supernovae, galaxy clustering and gravitational lensing to better understand dark energy and cosmic structure. The Dark Energy Spectroscopic Instrument is measuring the redshifts of millions of galaxies and quasars, building a three-dimensional map of the universe that can refine baryon acoustic oscillation measurements. The Vera C. Rubin Observatory will repeatedly survey the sky in extraordinary detail, discovering supernova, mapping dark matter through weak lensing, and tracking changes across time. The European Space Agency's Euclid mission is studying dark energy, dark matter, galaxy clustering, and gravitational lensing from space, where the view is beautifully clear and not interrupted by weather, atmosphere, or someone forgetting to close a dome. These projects matter because some tensions may fade with better data. A disagreement can sometimes come from calibration errors, selection effects, dust, instrument limitations, or assumptions that seemed harmless until the measurements became precise enough to notice them. In that case, improved observations may bring different methods into agreement. The tension does not become a revolution. It becomes a lesson in measurement. But some tensions may grow stronger. If better data confirms that different methods truly disagree, then scientists must consider new physics. Perhaps dark energy changes over time. Perhaps the early universe contained an extra energy component. Perhaps dark matter behaves in a more complicated way than assumed. Perhaps gravity itself needs adjustment on the larger scales. None of these possibilities should be accepted lightly, because the standard model has earned its strength. But none should be dismissed simply because they are inconvenient. This is the emotional center of the question. The universe may not be older than we think in the simple sense of adding a few billion years to the cosmic clock. the strongest evidence still supports an age close to 13.8 billion years within the Standard Model. But the question remains scientifically valuable because it tests the deepest map of cosmic history. It forces every method to meet the others. It asks whether ancient light, nearby stars, distant supernova, galaxy patterns, gravitational lensing, and ripples in space-time all tell the same story. When they do, the story becomes stronger. When they do not, the universe becomes more interesting. A cosmic disagreement is not a crack in the ceiling. It is a doorway into better understanding. It reminds us that science is not a list of finished facts, but a careful way of listening when reality refuses to be quite as simple as expected. The age of the universe may remain the same, but the path to understanding the age may lead through darker energy, stranger beginnings, and measurements so precise that even a tiny mismatch can echo across all of time. So, is the universe really older than we think? The most responsible answer is, not in the simple, proven sense. The strongest current evidence still supports a universe that is about 13.8 billion years old, at least when described within the standard cosmological model. That estimate is not a loose guess or a number chosen because it sounds suitably ancient. It comes from the cosmic microwave background, the expansion history of space, the distribution of galaxies, the measured contents of the universe, and the lambda cold dark matter model that ties these observations together. That is the firm ground. The universe appears to have been expanding from a hot, dense early state for about 13.8 billion years. The cosmic microwave background gives one of the strongest anchors for that conclusion. The oldest stars and globular clusters generally fit inside that timeline once their uncertainties are properly included. The broad pattern of galaxies across the cosmic web also makes sense within a universe of that age. In other words, the familiar number has not been casually knocked over by a few awkward galaxies and one suspiciously busy black hole. But the story around that number is not perfectly finished. The Hubble tension remains one of the clearest signs that something may not be fully understood. Measurements based on the early universe tend to suggest one present-day expansion rate, while measurements based on Cepheid variable stars, Type 1 are supernovae, and the local distance ladder tend to suggest another. This disagreement may eventually be explained by subtle measurement issues. It may also point toward new physics. Either way, it reminds scientists that cosmic age is not measured by simply reading a clock. It is inferred through a model of how space has expanded across time. Ancient stars offer a different kind of check. Stars such as HD 140283, the Methuselah star, have sometimes seemed uncomfortably old. Globular clusters also preserve populations of stars from the early history of galaxies. Yet these objects usually do not prove that the universe is older. Their ages depend on distance, brightness, chemical composition, and stellar evolution models. When those uncertainties are treated carefully, the older stars become less like contradictions and more like stress tests. They ask whether the timeline is strong enough to hold them, and so far, it generally is. Then come the early galaxies. The James Webb Space Telescope has revealed galaxies from very young cosmic times, some surprisingly bright, massive, dusty, or organized. Deep field programs such as JADES have pushed observations back to only a few 100 million years after the Big Bang. Galaxies such as JADES GSS13-1 show that structure was already appearing very early. This does not mean cosmology has been broken. It means the early universe may have formed stars and galaxies faster, more efficiently or more unevenly than many expectations allowed. That distinction matters. A galaxy can look old in a developmental sense without requiring the universe itself to be older in clock time. Stars, dust, heavy elements, disks, bars, and central black holes all take time to form, but the young universe may have provided extreme conditions. Gas was denser. Dark matter halos were growing. Star formation may have happened in intense bursts. The first stars may have lived brief lives and enriched their surroundings quickly. Early black holes may have started from large seeds or grown through rapid accretion. The first few 100 million years may have been far busier than once imagined. Rionization adds another layer. After the cosmic dark ages, ultraviolet light from the first stars, galaxies, and possibly black holes transform neutral hydrogen across space. If some early galaxies cleared large bubbles in the surrounding cosmic fog sooner than expected, then scientists must understand how those sources became so powerful so quickly. Again, the issue is not automatically extra time. It may be faster formation, more efficient radiation escape, dense environments, or details in the models that need improvement. There is also a deeper theoretical question. The age of 13.8 billion years refers to the observable universe since the hot, dense, expanding phase described by the Big Bang model. It does not necessarily answer what, if anything, came before that phase. Cosmic inflation, associated with Alan Guth, Andrei Lind, and Alexei Starobinsky, may describe an extremely rapid early expansion before the hot Big Bang phase as usually discussed. Speculative frameworks such as bouncing cosmology, cyclic cosmology, and Roger Penrose's conformal cyclic cosmology ask whether the observable universe might be part of a deeper history. These ideas are not established evidence that the universe is older. They are serious but uncertain attempts to explore what may lie beyond the earliest reliable boundary of current models. The observable horizon also keeps the question humble. The observable universe is not necessarily the whole universe. It is the region from which light has had time to reach us. Its radius is roughly 46 billion light-years because space expanded while light travelled, even though the age of the universe is about 13.8 billion years. There may be more universe beyond what can ever be seen from here. But a larger universe is not the same thing as an older universe. It simply means our measurements are made from inside a limited window, using signals that have managed to arrive, so the answer becomes more subtle than yes or no. The universe has not been proven older than 13.8 billion years in the standard observational sense, but parts of its early history may have unfolded faster than expected. Some structures may have formed under physical conditions that are not yet fully understood. The expansion history may contain ingredients that current models describe only approximately, and the hot Big Bang may not be the final word on whether reality has a deeper prehistory. That is where the real mystery lives, not in the claim that scientists have simply got the age wrong, but in the possibility that the number is only the beginning of a richer question. The universe may be the age the standard model says it is, while still having an early life more intense, more efficient, and more complex than expected. Or it may eventually require a refined model that changes how cosmic age is interpreted. Uncertainty here is not an empty space waiting to be filled with fantasy. It is an invitation to measure more carefully. It is the quiet pressure that makes better telescopes, deeper surveys, sharper models, and more patient questions. The universe may not be older in the simplest sense, but it remains old enough to keep its first moments partly hidden, and generous enough to leave clues in the light still crossing the dark. The age of the universe is one of the most impressive achievements of modern cosmology, and also one of its most humbling measurements. To say the universe is about 13.8 billion years old is not to make a casual guess in the dark. It is to gather ancient light, expanding space, stellar ages, galaxy observations, and the lambda cold dark matter model into one careful, testable picture. That picture remains powerful. The cosmic microwave background still gives scientists one of the deepest anchors for the age of the observable universe. The expansion history of space, the older stars, the structure of galaxies, and the success of the standard cosmological model all point toward the same broad answer. 13.8 billion years is not a fragile number, even if it is surrounded by fragile questions, and those questions matter. The Hubble tension suggests that different ways of measuring expansion do not yet fit together perfectly. The James Webb Space Telescope has found early galaxies that look surprisingly bright and developed. Some black holes seem to have grown enormous very quickly. Rionization may have begun with sources that cleared the cosmic fog earlier or more efficiently than expected. And beyond the hot Big Bang, science still cannot say with certainty whether there was a deeper beginning, a previous phase, or no before in any familiar sense. So perhaps the universe is older in a way current models do not yet capture, or perhaps it is exactly the age the best evidence suggests, while its earlier structures formed faster than once imagined. Either answer would be extraordinary. For now, humanity keeps measuring ancient light from inside the universe itself, trying to understand not only when everything began, but what beginning means when space and time are part of the story.